Imagine looking up at the night sky, feeling the infinite vastness of the universe. But have you ever wondered, will Earth, our beloved home, exist forever? Or is it merely a tiny speck in the relentless journey of time and space, awaiting an inevitable end? In this 4-hour journey, we will uncover earth-shattering secrets about our planet and the distant realms of the cosmos. From how modern science holds the power to destroy an entire planet to the miraculous story of the formation of primordial oceans, the cradle of life. We'll travel through the Great Lakes of North America, explore the rapidly changing atmosphere, and ultimately confront the inescapable fate of Earth as the sun expands into a red giant. The universe is a never-ending book, and today we will turn its most captivating pages to understand where we came from, where we are, and where we are ultimately headed. How to kill a planet. Introducing ways to destroy the Earth with modern science and physics. Have you ever thought that Earth, a planet that has existed for 4.2 billion years, surviving harrowing challenges like giant meteor collisions and violent volcanic eruptions, could now face a threat from the very creations of humanity? This planet has witnessed the most brutal moments in the history of the universe, from successive meteor impacts in its early days to massive volcanic eruptions that blanketed the skies in darkness for millions of years. These events not only reshaped the geological structure of the Earth, but also drove evolution, transforming simple unicellular organisms into today's rich and diverse ecosystems. This resilience has fostered the belief that Earth is an unassailable fortress, a place immune to upheaval. However, the new threat doesn't arise from nature, but from human hands. With the remarkable advances in science and technology, humans have developed tools of incredible power, yet fraught with unimaginable risks. Particle accelerators, like the Large Hadron Collider, are not only symbols of human ingenuity, but also capable of recreating conditions akin to the universe's state immediately after the Big Bang. Nuclear technology, once heralded as a sustainable energy source, harbors the potential to release energy far surpassing any natural phenomenon. These innovations, if not meticulously controlled, could plunge the planet into catastrophe. Such potent tools not only revolutionize human understanding of the universe, but also present an unprecedented challenge regarding the responsibility of wielding scientific power. Consider a specific example to understand this risk more clearly. In 1945, the nuclear bomb Little Boy devastated Hiroshima with a blast equivalent to 15 kilotons of TNT. But that pales in comparison to modern nuclear weapons, which are thousands of times more powerful, reaching megaton levels of TNT. If an uncontrolled nuclear chain reaction were to occur, the consequences could rival the disaster caused by the massive asteroid that wiped out the dinosaurs 66 million years ago. Such an event wouldn't just destroy habitats, but could push the entire ecosystem to the brink of collapse. These challenges raise a serious question about humanity's responsibility. While Earth has endured the harshest natural disasters, it is now humans, with artificial technology, who pose an unprecedented risk to the planet. This calls for careful deliberation on how we use scientific power, not only to protect the planet, but also to safeguard our own future. We have the capability to create magnificent tools to explore and understand the universe, but simultaneously, we must ensure these tools do not become the greatest threat to the home we call Earth. What would happen if Earth were pulled into a black hole, torn apart by antimatter, or crushed by a massive asteroid larger than Everest? This is not a question from a science fiction movie, but rather scenarios studied and simulated by scientists and physicists based on extreme physical and astronomical phenomena. The purpose is not only to understand the universe, but also to anticipate potential threats to the existence of our planet. These scenarios not only ignite imagination, but also serve as warnings of possible dangers in a universe filled with uncertainties. One of the most terrifying scenarios is the appearance of a black hole near Earth. A black hole, with its immense gravitational force, can pull in all surrounding matter and compress it to the point where even light cannot escape. If a wandering black hole were to pass through the solar system, not just Earth, but all the planets could be drawn in, torn apart by its immense power. Although the probability of such an event is extremely low, the existence of wandering black holes has been documented, heightening concerns about this apocalyptic scenario. Another scenario involves antimatter, a special type of matter capable of annihilating regular matter upon contact, releasing an enormous amount of energy. In physics experiments, antimatter is produced in extremely small quantities. But if future technology allows for large-scale production of antimatter, the risk would become significant. Imagine if a large amount of antimatter were activated at Earth's core. The resulting annihilation reaction would produce a massive explosion capable of destroying the entire planet, turning it into a blazing fireball. Additionally, scientists warn about the threat posed by massive asteroids. History has shown that asteroids are not a distant threat. An asteroid only a few kilometers in diameter, similar in size to the one that wiped out the dinosaurs 65 million years ago, could have catastrophic consequences. This scenario occurred when an asteroid about 10 kilometers in diameter collided with Earth, creating the Chicxulub crater in Mexico. The impact released energy equivalent to billions of nuclear bombs, causing massive tsunamis and blanketing the atmosphere with dust and toxic gases, leading to mass extinction. These seemingly distant scenarios are all constructed based on real scientific data and simulations, from studying black holes to tracking near-Earth asteroids. However, the goal is not to spread fear, but to raise awareness of humanity's role in protecting the planet. Scientists have developed monitoring and research systems to detect cosmic threats early, such as the NEOWISE program, which tracks near-Earth objects. These scenarios, though terrifying, not only serve as warnings, but also demonstrate humanity's capacity for understanding and controlling extreme cosmic phenomena. Earth, a planet that has survived the harshest challenges, still needs vigilance from humanity to endure in a universe filled with unforeseen dangers. This reminds us that while the universe offers wonders, it also harbors threats that we must be prepared to face. Why do scientists spend time and resources simulating seemingly far-fetched doomsday scenarios for Earth? To many, such studies may seem unnecessary or even entertaining, but in reality, they hold profound and practical significance. The goal is not only to test the limits of natural forces, but also to gain a deeper understanding of how the planet and the universe operate, while alerting humanity to potential dangers from both the cosmos and human activities. When physicists simulate scenarios like Earth being pulled into a black hole or torn apart by antimatter, they are not merely exploring extreme possibilities, but also studying the fundamental principles that govern the existence of all matter in the universe. A black hole, with its immense gravitational force, may pose a potential threat if it were to appear near the solar system. But it is also a crucial subject for scientists to understand how space-time operates. Similarly, antimatter, with its ability to annihilate regular matter and release vast amounts of energy, not only provides insights into the origins of energy, but also hints at potential applications in future scientific and technological fields. These studies go beyond exploring the limits of nature to serve as warnings to humanity about risks created by humans themselves. Nuclear technology, massive particle accelerators, and ambitious scientific endeavors such as asteroid mining offer great potential, but come with unforeseen risks. Asking questions like, "What happens if we go too far?" is not just an intellectual exercise, but a necessary reminder. Such research keeps humanity mindful of its scientific ambitions, ensuring that we always consider the ethical responsibilities of wielding power. A notable example of such research is the use of particle accelerators to recreate conditions immediately after the Big Bang. These powerful tools allow us to explore the origins of the universe, giving humanity a better understanding of the first moments of its formation. However, scientists are also aware of potential risks, such as the possibility of creating an artificial black hole or triggering phenomena not yet fully understood. Such studies, though theoretical, help humanity better understand the boundaries of science and the risks we might face in our quest for discovery. These seemingly unimaginable scenarios are not mere products of imagination, but are grounded in real scientific data. They not only illuminate fundamental physical principles, but also serve as warnings about humanity's responsibility in using science and technology safely. From developing world-changing technologies to pursuing space exploration ambitions, these studies remind us that scientific power always comes with ethical responsibility. In other words, researching Earth's destruction scenarios is not just an act of discovery, but a necessary reminder of vigilance and responsibility. In a world where science and technology are advancing rapidly, these studies serve as a precautionary measure, ensuring that humanity does not inadvertently cause irreversible consequences. Our planet has endured billions of years of natural challenges, but to continue its existence, we must ensure that our scientific knowledge is applied safely, ethically, and for the benefit of our shared future. Potential catastrophes, black holes, antimatter bombs, and asteroid impacts. Could black holes, the invisible monsters of the universe, swallow Earth and obliterate all life in an instant? This is not a question from a science fiction movie, but a profoundly challenging scenario based on real scientific understanding of one of the most bizarre and terrifying phenomena in the universe. Black holes are formed when massive stars exhaust their fuel and collapse under their own gravity. The result of this collapse is a region of space with such immense gravitational force that nothing, not even light, can escape. With such colossal pull, black holes not only affect nearby objects, but also distort space and time itself. Imagine a black hole the size of a ping-pong ball, but with a mass equivalent to Earth. Such an object could cause a global catastrophe if it approached our planet. The black hole's extreme gravity would stretch and fracture Earth before consuming all matter into its singularity. Every form of life, structure, and the atmosphere would be ripped apart by its immense gravitational force. An even more terrifying scenario arises if a larger black hole, with a mass several times that of the Sun, were to approach the solar system. In this case, not only Earth, but all the planets in orbit would spiral into chaos. The black hole's immense gravity would disrupt planetary orbits, leading to collisions or complete annihilation. Even light from the Sun would fail to escape its grasp. A striking example of the power of black holes is Sagittarius, a star, the supermassive black hole at the center of the Milky Way. With a mass 4 million times that of the Sun, it currently lies more than 26,000 light-years away from Earth. Although safely distant, Sagittarius A star serves as a reminder of the potential danger posed by black holes. If a black hole of similar size appeared within a few light-years of Earth, our planet would be doomed. All life would end before we could take any measures to counter it. Black holes are a clear demonstration of the universe's unimaginable power, reminding humanity of its insignificance in the grand cosmic scheme. Although there are no signs of a black hole appearing near Earth in the foreseeable future, their existence is a stark warning that we are but a tiny part of an immense and perilous universe. Studying and understanding black holes not only allows humanity to uncover the mysteries of the cosmos, but also mentally prepares us for potential doomsday scenarios, albeit with the hope that they will never materialize. Earth, resilient through billions of years of existence, still faces threats from the vast expanse of the universe that humanity is only beginning to comprehend. Did you know that just 1 gram of antimatter could release energy equivalent to tens of thousands of tons of TNT? This may sound like science fiction, but in reality, antimatter is a special and highly potent form of matter that also carries great risks. Antimatter is the opposite counterpart of regular matter. While particles such as protons in ordinary matter carry a positive charge, in antimatter they carry a negative charge and are called antiprotons. Similarly, electrons in ordinary matter have a negative charge, but in antimatter their charge is reversed to positive, earning them the name positrons. When matter and antimatter come into contact, they annihilate each other, converting their entire mass into energy. As described by Einstein's famous equation, E equals mc squared, E equals mc2, E equals mc squared. With its immense energy release capability, antimatter is often touted as an ideal energy source for the future. A small amount of antimatter could power an entire city or spacecraft for extended periods. However, the darker side of this potential lies in its use as a theoretical weapon, with destructive power far surpassing any current technology. To completely destroy Earth, scientists estimate it would require a bomb containing several thousand tons of antimatter. If detonated, such a bomb would trigger a chain reaction, releasing energy sufficient to vaporize the planet's surface, destroy its internal geological structure, and reduce Earth to a cloud of dust drifting through space. While this scenario sounds terrifying, producing such a large quantity of antimatter remains impossible with today's technology. The production and storage of antimatter pose extraordinarily complex scientific challenges. In modern particle accelerators, such as the Large Hadron Collider, LHC, antimatter is created by accelerating particles to extremely high speeds and allowing them to collide. However, only a minuscule amount of antimatter is produced in these experiments, sufficient for scientific study, but not enough to pose any danger. Furthermore, antimatter cannot exist naturally, as it would immediately annihilate upon contact with any surrounding matter. Thus, storing and controlling antimatter is a technological puzzle that remains unsolved. An intriguing example of antimatter's application is in medical technology, specifically positron emission tomography, PET. PET uses positrons, a type of antiparticle, to generate detailed internal images of the body, aiding in the diagnosis of serious conditions like cancer. This demonstrates that antimatter is not always a threat, but can yield significant benefits when used correctly. However, achieving the energy scale required to destroy Earth would demand technology far beyond what is currently feasible. Antimatter is one of the clearest examples of humanity's creativity and intellect, while also serving as a reminder that scientific power always comes with responsibility. Although antimatter holds immense potential to revolutionize how humans harness energy, it also carries significant risks if misused. For now, antimatter remains within the realm of theoretical research and limited practical applications. But in the future, if technology evolves to control antimatter on a large scale, humanity will face an ethical dilemma: in harnessing this power? Will it become an infinite energy source, driving unprecedented progress? Or a destructive weapon putting the planet at risk of annihilation? Only time and human wisdom can answer this question. 65 million years ago, a massive asteroid struck Earth, ending the reign of the dinosaurs and wiping out 75% of life on the planet. But what if a larger, faster asteroid were to collide with Earth today? This question is not just for the imagination, but represents a real concern that scientists continuously monitor and study. Asteroids, space objects ranging in size from tiny grains of sand to ones larger than entire cities, have the potential to cause catastrophic destruction when they impact a planet. The energy released from such a collision could shake the entire ecosystem, trigger mass extinctions, and induce climate change lasting centuries. Even an asteroid just a few kilometers in diameter could cause a global disaster. Upon impact, shock waves would radiate outward at supersonic speeds, destroying everything within hundreds of kilometers. Massive tsunamis would engulf coastal regions, while dust and debris from the explosion would rise into the atmosphere, blocking sunlight for years. This would not only lower global temperatures, but also disrupt photosynthesis, collapsing natural food chains. The colossal impact event at the Yucatan Peninsula in Mexico, where an asteroid created the Chicxulub crater, serves as a stark example. The energy released from this collision was equivalent to billions of atomic bombs, triggering a chain reaction of destruction that the ecosystem of that time could not recover from. However, it's not just large asteroids that pose a threat. The Chelyabinsk event in 2013 is a reminder that even smaller asteroids can cause significant damage. This asteroid, with a diameter of just about 20 meters, exploded in the skies over Russia, generating a shockwave strong enough to shatter windows in thousands of buildings and injure over 1,500 people. While it did not cause geological damage, the event was a stark reminder that smaller asteroids, though not capable of vaporizing Earth's surface, can still wreak havoc on human life and infrastructure. Earth constantly faces threats from asteroids, ranging from tiny fragments that burn up in the atmosphere to massive objects capable of wiping out entire civilizations. According to NASA data, thousands of small asteroids enter the atmosphere each year, creating the streaks of light we call meteors. However, larger asteroids with the potential to cause global disasters still exist and traverse space, posing a threat to our planet. In response, NASA and other international space agencies have initiated several projects to detect and deflect dangerous asteroids. One notable effort is the DART Double Asteroid Redirection Test mission, designed to test the capability to alter the trajectory of an asteroid on a collision course with Earth. The success of DART is not just a technological milestone, but a beacon of hope for humanity's survival against space-based threats. Asteroids are not merely harmless space rocks, but serious reminders of Earth's fragility. Although significant progress has been made in detection and prevention, no one can guarantee that one day a massive asteroid won't head straight for our planet. This reality demands that humanity continue investing in research, developing defense technologies, and remaining vigilant against unexpected threats from the vast universe. Over billions of years, Earth has endured numerous asteroid catastrophes. But can it withstand another challenge if faced with a larger, more devastating impact? The answer depends on what actions we take today. Birth of the oceans. Exploring the formation of Earth's oceans. Did you know that Earth was once a molten fireball, devoid of water, life, and completely different from the vibrant blue planet we see today? Around 4.5 billion years ago, When Earth first formed, it bore no resemblance to its current state. Instead of cool oceans and a life-supporting atmosphere, the planet was a molten mass of rock covered in lava and enveloped by a toxic atmosphere filled with gases like carbon dioxide, methane, and ammonia. This was Earth's chaotic infancy, a time when its surface was unformed and the planet was continuously bombarded by violent collisions with asteroids and smaller planetary bodies in the early solar system. Earth's surface at that time resembled a geological nightmare. Continuous volcanic eruptions sent streams of molten lava cascading across the terrain. Constant impacts from asteroids, some as large as small planets, added to the chaos. These collisions not only generated immense heat, keeping the planet in a molten state, but also delivered new materials, shaping Earth's geological structure. Some of these asteroids carried crucial elements that would later form the foundation for the planet's outer crust. At this stage, water, the essential ingredient for life, was completely absent. Surface temperatures on Earth were so high that any water vapor present would immediately evaporate, leaving no chance for oceans to form. Regions that now hold vast seas and deep lakes were then fiery, molten expanses, perpetually shifting due to internal planetary forces. The oceans we know today, where life first emerged, were an unimaginable reality at this point. One significant event from this era was the hypothesized collision with a large celestial body, often referred to as Theia. This impact not only reshaped Earth's structure, but is also believed to have formed the Moon. Scientists theorize that debris from this collision was captured by Earth's gravity and coalesced to form our planet's only natural satellite. This event highlights the destructive yet foundational role collisions played in shaping early Earth, while underscoring their importance in laying the groundwork for the planet as we know it today. Earth's early stages were anything but calm or peaceful. It was a time dominated by extreme heat, meteor impacts, and violent geological activity. Yet, these seemingly uninhabitable conditions laid the groundwork for the planet's evolution. The collisions brought in new materials that contributed to the formation of the initial crust and atmosphere. Over millions of years, as temperatures gradually decreased, conditions began to change, paving the way for the emergence of water, an essential element for sustaining life. The transformation from a seething, evaporative mass of rock to the lush, life-filled planet we see today is a testament to Earth's ability to adapt and transform. Reflecting on this early period not only provides insight into the planet's history, but also demonstrates that even from the harshest conditions, life can find a way to begin. Earth, 4.5 billion years ago, with its churning lava flows and suffocating atmosphere, marked the starting point of a grand journey. A journey that eventually led to the thriving life we enjoy today. How did Earth transition from a molten fireball to producing its first drops of water? The source of all life. The story of water's formation on our planet began as Earth entered its cooling phase. From a blazing mass of molten rock covered in lava and toxic gases, the planet gradually transformed, creating the first environment capable of retaining liquid water, laying the foundation for the development of life. Around 4.4 billion years ago, as Earth began to cool, a thin, solid crust started forming on its surface. Volcanic eruptions continued, but instead of only spewing lava, they released massive amounts of gases into the primordial atmosphere. These gases, including water vapor, carbon dioxide, and sulfur dioxide, formed a thick atmospheric layer surrounding the planet. Among these, water vapor played a particularly critical role. Previously, Earth's surface temperatures were so high that any water vapor immediately evaporated. But as the planet cooled, water vapor in the atmosphere began to condense into tiny droplets. A pivotal moment marking the shift from a barren, dry world to one with the potential for water. This process didn't happen overnight. It spanned millions of years. During this time, Earth underwent significant geological transformations. Chemical reactions between water vapor, the carbon dioxide-rich atmosphere, and the molten rocky crust created new compounds, contributing to the atmospheric composition. Gradually, tiny water droplets accumulated and merged into larger pools, eventually forming primordial lakes. These lakes not only stored water, but also acted as natural chemical reactors, where the first organic compounds could form, laying the groundwork for life. An important factor driving water condensation was the uneven cooling across the planet's surface. Lower-lying areas, less affected by volcanic activity, tended to collect water more quickly. Condensed water fell to the surface and flowed into these low-lying regions, creating the first reservoirs. Over time, these water bodies expanded as more condensed water accumulated. Through this process, Earth transitioned step by step from a seething mass of molten rock into a planet with the presence of water, a vital ingredient for life. This condensation process can be easily illustrated by a familiar everyday phenomenon. Imagine placing a cold glass of water in a warm room. Water vapor in the air begins to condense on the glass's surface, forming tiny droplets. On a planetary scale, this process occurred similarly, but on a vastly larger scale. As atmospheric temperatures dropped below the threshold for water vapor to remain in its gaseous state, it condensed into the first droplets of water. These droplets symbolized not only a physical transformation, but also the beginning of Earth's long journey to becoming the vibrant blue planet it is today. The emergence of liquid water on Earth was a monumental milestone in the planet's history. Those initial tiny droplets accumulated into pools, lakes, and eventually vast oceans that now cover most of Earth's surface. Water not only moderated the harsh environment, but also paved the way for more complex chemical reactions, leading to the formation of the first organic molecules, the precursors of life. From a fiery and chaotic planet, Earth transformed, gaining the ability to store and sustain life. The condensation of water vapor stands out as one of the most critical turning points in Earth's planetary evolution. It marked the beginning of a new era, where Earth began to take shape as a hospitable home for life. From those first droplets of water, the planet underwent billions of years of transformation, forming expansive oceans and diverse ecosystems. This is not just a story of planetary evolution, but a testament to nature's miraculous ability to create the perfect conditions for life to emerge and thrive. Did you know that the vast blue oceans we see today, covering over 70% of Earth's surface, once began as small pools on a chaotic planet? The story of how the oceans formed spans millions of years, beginning with the first droplets of water and the continuous contributions from outer space. This process not only shaped the planet's appearance, but also created the conditions for life, transforming Earth into the ideal home for living organisms as we know it today. After Earth began cooling, the first droplets of water condensed from an atmosphere rich in water vapor, carbon dioxide, and other gases. These droplets did not remain stationary, but flowed through cracks and low-lying areas on the planet's scorching surface, forming small streams and pools. But the journey of water did not end there. Over the following millions of years, these small pools continued to merge, expand, and deepen due to the increasing amount of water contributed by the atmosphere. Continuous condensation, along with prolonged rainfall over millennia, transformed the small pools into lakes and early seas. In addition to this natural accumulation, another crucial factor contributed significantly to the increase in Earth's water supply: meteorites. During the early solar system, Earth was frequently bombarded by meteorites and comets. Among them, carbonaceous chondrite meteorites carried water-rich compounds like H2O and organic molecules. When these meteorites collided with Earth's surface, the water and compounds they carried were released, adding to the planet's water reserves. These intense collisions not only delivered water, but also altered the planet's geological structure, creating larger basins where water could gather and accumulate. Modern scientific studies have shed light on the role of these meteorites in forming Earth's oceans. Analyses of carbonaceous chondrite meteorites reveal that they contain significant amounts of water and essential organic compounds for life. This not only explains how Earth amassed its vast water supply, but also raises questions about whether similar meteorites played a comparable role on other planets in the universe. The journey of water from space to Earth, combined with the condensation process on the planet's surface, created the immense volumes of water necessary to form the oceans we see today. On early Earth, water began collecting in large basins formed by meteorite impacts or the movement of the planet's crust. These basins gradually expanded and deepened, fed by streams from smaller water sources, heavy rains, and other geological processes. Over millions of years, small seas merged into the first vast oceans that covered much of the planet's surface. This transformation was not just a change in Earth's shape and structure, but a pivotal moment in its history, as water is essential for sustaining and fostering life. This phenomenon can be compared to how small droplets flow through cracks in rocks to form streams, which then grow into rivers and lakes. However, on a planetary scale, this process spanned millions of years and was influenced by factors such as temperature, geological activity, and meteorite impacts. The initial small pools of water, with the help of time and natural elements, turned Earth from a barren planet into a thriving world with expansive oceans. The formation of Earth's oceans is a miraculous journey, not the result of a single event, but a culmination of numerous processes occurring over millions of years. From the first tiny droplets to small pools, from primordial seas to vast oceans, Earth underwent a long evolution to become the water-rich planet it is today. The oceans not only add immense beauty to the planet, but also serve as the cradle of life, where the first crucial chemical reactions occurred. Their existence is a testament to the power and creativity of nature, reminding us of the challenging yet extraordinary journey of the planet we call home. The role of volcanoes and water vapor, evaporation in the primordial atmosphere. Did you know that volcanoes, often seen as symbols of destruction, were actually one of the most crucial factors in shaping Earth's first atmosphere? In the early chaotic stages of our planet, when Earth was a molten mass of searing heat, volcanic activity was intense and relentless. These continuous eruptions not only reshaped the planet's surface, but also played a vital role in releasing gases from the Earth's interior, forming the first atmosphere, an essential prerequisite for the emergence and development of life. During Earth's first few million years, volcanic eruptions released enormous amounts of gases, such as water vapor, H2O, carbon dioxide, CO2, sulfur dioxide, SO2, and methane, CH4, into the nascent atmosphere. These gases formed the basic components of the primordial atmosphere, creating a protective layer that retained heat and enabled crucial chemical reactions. Among them, water vapor was the most abundant, forming dense clouds that enveloped the entire planet. As Earth cooled, this water vapor condensed into droplets, laying the foundation for the formation of small pools of water and, over time, vast oceans. Carbon dioxide, which today is often regarded as a primary driver of climate change, played a vital role during that period. It helped stabilize Earth's surface temperature by preventing rapid heat loss. The CO2-rich atmosphere created an early greenhouse effect, trapping heat from the sun and the planet itself, allowing Earth to cool gradually rather than freezing abruptly. This slow cooling was critical because, without it, liquid water could not have existed, making it nearly impossible for life to develop. Additionally, sulfur dioxide, SO2, and methane, CH4, released by volcanoes, also contributed to shaping the early atmosphere. SO2, a highly reflective gas, formed aerosols and dust particles in the atmosphere, reducing the amount of sunlight reaching Earth's surface and counterbalancing the greenhouse effect of CO2. Methane, a more potent greenhouse gas than CO2, retained heat in the atmosphere and further stabilized temperatures, creating conditions favorable for the appearance of liquid water. A striking example of the critical role volcanoes play in shaping atmospheres can be observed on Io, one of Jupiter's moons. Io, known for its intense volcanic activity, continuously ejects gases into space, much like how early Earth's volcanoes pumped gases into the atmosphere. Early Earth likely experienced a similar phase, where gases released from the interior not only formed the atmosphere, but also influenced the planet's chemical composition. Volcanic activity was not merely a series of isolated destructive events. It was, in fact, Earth's first atmosphere-building machine. Volcanoes provided the essential chemical components for life, shaping the climate and the early environment of the planet. Through relentless eruptions, Earth transitioned from a monotonous molten mass into a planet with a diverse atmosphere, paving the way for the formation and maintenance of liquid water. This process highlights the irreplaceable role of volcanoes in shaping Earth's future. Without the vigorous volcanic activity of its early stages, Earth likely would not have developed a water vapor and CO2-rich atmosphere, essential factors for retaining heat and creating conditions suitable for life. Today, although we often perceive volcanoes through the lens of destruction, Earth's distant memories remind us that these fiery mountains laid the foundation for life itself, transforming Earth from a barren rock into a vibrant and colorful planet. From the dense clouds of water vapor released by primordial volcanic eruptions, how did Earth generate its first rain, the beginning of today's vast oceans? The story of rain on Earth is not merely a simple climatic phenomenon, but a crucial turning point in the planet's history, leading to fundamental changes in its surface structure and creating conditions for the emergence of life. As Earth entered its cooling phase after a chaotic period, water vapor from volcanic eruptions was retained in the atmosphere by the planet's strong gravitational pull. This gravitational force prevented the water vapor from escaping into space, as occurred on other planets in the solar system, such as Mars. Mars, with its weaker gravity, failed to hold on to its atmosphere and water vapor, while Earth succeeded in trapping the vast amounts of water vapor around it. This vapor, along with gases like carbon dioxide and methane, formed a thick atmosphere that retained heat and slowed the planet's cooling process. As Earth continued to cool, surface temperatures dropped below the threshold for water vapor to remain in its gaseous state. The water vapor in the atmosphere began to condense into tiny droplets, coalescing into large clouds. This marked the precursor to Earth's first rains. The droplets, influenced by gravity, started falling to the surface, initiating an entirely new cycle. These rains were not brief showers, but continuous downpours lasting millions of years, with massive amounts of water gradually covering the planet's surface. The prolonged and intense rains became a major force in reshaping Earth's surface. Rainwater flowed into valleys and basins, filling natural depressions and forming pools, lakes, and eventually primordial oceans. The previously barren and lava-covered surface of Earth began transforming into a planet with its first large bodies of water. Water not only cooled the surface, but also interacted with the planet's chemical compounds, enabling critical chemical reactions. These were the initial steps toward creating an environment capable of supporting life. To better understand this process, consider a familiar phenomenon. When you boil water, the steam rises and condenses into droplets on the lid. On a planetary scale, Earth's atmospheric water vapor acted like a giant lid. As the vapor condensed, it not only cooled the planet, but also triggered heavy rains that helped shape its surface and allowed liquid water to exist on a large scale. Beyond bringing water back to the surface, these relentless rains also contributed to regulating Earth's atmospheric and surface temperatures, creating the thermal balance necessary for long-term planetary stability. Streams of rainwater carried dust and minerals, enriching the chemistry of the early pools and lakes. This set the stage for the formation of essential organic compounds, marking the initial phase of biological evolution. The process of condensation and rainfall lasted millions of years, but its impact on Earth's history cannot be overstated. From the fragile early clouds of water vapor, the planet gradually developed larger water bodies that eventually became the oceans, covering over 70% of Earth's surface today. These oceans were not only the birthplace of life, but also crucial in regulating climate, sustaining life, and shaping the planet's landscape. Condensation and rain were not merely natural climatic events, but decisive milestones in Earth's evolution. The first rains opened a new chapter in the planet's history, returning water from the atmosphere to the surface, while facilitating the first chemical and biological reactions. Thanks to this process, Earth transformed from a barren and chaotic planet into a water-rich world, complete with vast oceans, the cradle of life. Have you ever wondered how Earth transformed from a molten surface into a stable planetary crust that allowed water to exist and develop into oceans as we know them today? The answer lies in the critical role of volcanic eruptions, not only in supplying water, but also in shaping the geological crust and stabilizing the planet's surface. These processes laid the necessary foundation for the maintenance of liquid water, paving the way for life. In its primordial phase, Earth was covered by a constantly shifting layer of molten lava driven by powerful volcanic eruptions. These eruptions not only released water vapor and gases like carbon dioxide and sulfur dioxide into the atmosphere, but also spewed lava across the surface. As the lava cooled, it solidified into layers of hard rock, forming the planet's first geological crust. This crust acted as a protective shield, separating the hot magma beneath from the surface and reducing the planet's overall temperature. The geological crust didn't just lower the surface temperature, it also provided a stable foundation for liquid water to exist. If Earth's surface had remained molten, any condensed water vapor would have immediately evaporated, preventing the formation of lakes, rivers, or oceans. The hardened crust, by stabilizing surface temperatures, allowed water vapor to condense and persist as liquid water. Depressions in the crust, formed by geological activity and meteorite impacts, became natural reservoirs for water, leading to the formation of pools, lakes, and eventually vast oceans. The stability of Earth's surface also played a crucial role in preventing water from seeping deep into the planet's interior. As the geological crust thickened and solidified, it not only retained water at the surface, but also slowed the rapid escape of internal heat. This maintained Earth's surface temperature at a level low enough for liquid water to exist yet warm enough to enable essential chemical reactions. These reactions, occurring between water and minerals in the crust, created a chemically rich environment that supported the development of organic compounds, the precursors of life. A clear example of the role of the geological crust can be seen in modern volcanic islands like Hawaii. On these islands, lava from volcanic eruptions cools and forms new layers of rock. These layers not only create stable surfaces, but also supply essential minerals for the formation of lakes, streams, and even diverse ecosystems. Hawaii is a vivid demonstration of how volcanoes not only shape, but also create environments that sustain and support water and life. On a planetary scale, volcanic eruptions were central to shaping the surface and forming the atmosphere, turning Earth from a molten mass into a water-retaining planet. Moreover, the geological crust became the foundation for tectonic processes, an essential mechanism for recycling and regulating the planet's surface, ensuring Earth's stability over billions of years. Volcanic eruptions were not merely destructive events. They were key to creating the conditions necessary for water's existence and growth. From cooling lava flows to the formation of a hardened geological crust, volcanic activity shaped the planet's surface, providing a stable base for liquid water to thrive. Without this crust, Earth could not have retained water, and without water, life as we know it today would not have been possible. Reflecting on Earth's journey from a molten mass to a water-rich planet, the role of volcanic eruptions and the formation of the geological crust becomes unmistakably clear. These transformations not only stabilized the planet's surface, but also paved the way for the appearance of water, the most vital resource for life. From there, Earth began its miraculous journey to become the living, vibrant home we know today. The origin of water from meteorites and water-bearing compounds from space. Have you ever considered that every drop of water you drink today might have come from meteorites and comets that collided with Earth billions of years ago? This idea is not just a hypothesis, but is supported by numerous scientific studies, revealing that most of Earth's water is not native to the planet, but arrived from outer space. Wandering through the solar system, meteorites and comets carrying large amounts of ice and organic compounds played a critical role in delivering water to early Earth, creating the essential conditions for life. When Earth first formed around 4.5 billion years ago, its surface was a molten mass with no trace of water. The water we see today originated from celestial bodies, primarily meteorites and comets. These objects, formed in distant regions of the solar system, contained frozen water along with elements like hydrogen and oxygen, the fundamental components of water. When they collided with Earth, the intense impacts released this water, along with other elements and compounds, initiating the formation of the atmosphere and the first oceans. This process was most active during a period in Earth's history known as the Late Heavy Bombardment, approximately 4 billion years ago. At this time, the solar system was in a state of chaos, with millions of meteorites and comets bombarding planets, including Earth. These impacts not only brought vast amounts of water, but also delivered critical chemical elements like carbon, nitrogen, and phosphorus, essential building blocks for life. While these collisions caused massive explosions and reshaped the planet's surface, they also acted as water ambassadors, transporting resources from space to Earth. A striking example of the role of comets in delivering water is Halley's Comet. one of the most famous comets observed in the solar system. Chemical analyses of fragments from Halley's Comet have shown that it contains significant amounts of water ice and organic compounds, key ingredients for life. Remarkably, the chemical structure of water found in Halley's Comet closely resembles that of Earth's water, strengthening the hypothesis that comets were major contributors to Earth's water supply. This is not an isolated case. Many other comets and meteorites have been discovered to carry water ice and organic compounds, underscoring their role in shaping the ecosystem of our planet. Carbonaceous chondrite meteorites, a specific type of meteorite rich in water, have also been identified as one of the primary water suppliers to Earth. When these meteorites collided with Earth, the ice within them melted due to the heat of the impact and the atmospheric pressure. This water was then absorbed into the planet's surface, accumulating over time to form lakes, rivers, and eventually vast oceans. These meteorites not only provided water, but also introduced the first organic molecules, laying the groundwork for the emergence of life. Meteorite and comet impacts were not merely destructive events as they are often perceived. In reality, they were constructive processes that delivered water and essential chemical components to Earth. Thanks to these contributions, the planet transformed from a searing, barren rock into a water-rich world, with oceans covering more than 70% of its surface, becoming the cradle of life. When we reflect on the role of meteorites and comets, we see not just destroyers, but also creators, bringing the vital resources necessary for life to flourish. These seemingly random collisions brought water, the most critical resource for life, to Earth, opening a new chapter in the history of both the planet and the universe. This reminds us that the life and environment we enjoy today are the results of cosmic events that took place billions of years ago, when the first drops of water arrived from these water ambassadors of space. How do scientists determine that water on Earth might originate from ancient meteorites in the solar system? The answer lies in advanced studies of hydrogen isotopes, a powerful tool for decoding the origin of water on our planet. Hydrogen isotopes, particularly the ratio between deuterium, heavy hydrogen, and regular hydrogen, serve as a unique chemical fingerprint that allows scientists to compare Earth's water with water found in celestial objects. Findings from these studies reveal a remarkable match between water on our planet and water discovered in carbonaceous chondrite meteorites, some of the oldest remnants from the early solar system. Carbonaceous chondrites are a specific type of meteorite rich in water and organic compounds. They are formed from the primordial materials of the solar system and have not undergone significant thermal or chemical alterations. This pristine nature makes them time capsules, preserving invaluable information about the early stages of the solar system. Studies of hydrogen isotopes in these meteorites show that their deuterium to hydrogen ratio closely aligns with that found in Earth's water. This provides strong evidence that the water on our blue planet may have been delivered by carbonaceous chondrites. But water is not the only contribution from these meteorites. Carbonaceous chondrites also contain essential organic compounds like amino acids, the building blocks of life. When these meteorites collided with early Earth, they not only released water, but also supplied critical elements and chemical compounds that catalyzed the first biological reactions. This helped form vast oceans while creating an ideal environment for early life to develop. A prime example of the role of carbonaceous chondrites is the Murchison meteorite, which fell to Earth in Australia in 1969. The Murchison meteorite contains not only water, but also dozens of naturally occurring amino acids. Detailed analysis of this meteorite revealed that the hydrogen isotope composition of its water closely matches that of Earth's water. reinforcing the hypothesis that meteorites were key transporters of water to our planet. Moreover, the organic compounds in Murchison demonstrate how the unique combination of water and chemicals carried by these meteorites could have sparked the emergence of life. The period known as the Late Heavy Bombardment, approximately 4 billion years ago, was a particularly crucial time in Earth's history. During this chaotic era, the solar system was bombarded by millions of meteorites and comets colliding with planets. Earth was relentlessly pummeled by carbonaceous chondrites during this period. These impacts not only delivered vast amounts of water, but also deposited vital chemical elements such as carbon, nitrogen, and phosphorus onto the planet's surface, laying the groundwork for the early chemical reactions that led to life. Hydrogen isotope studies not only provide scientific evidence for the origin of Earth's water, but also broaden our understanding of life in the universe. If meteorites and comets delivered water and organic compounds to Earth, they could have done the same for other planets. This raises an intriguing question. Could life emerge on other planets under similar conditions? Understanding carbonaceous chondrites not only helps decode the past of our planet, but also opens the door to exploring the possibility of life beyond the solar system. In summary, carbonaceous chondrite meteorites are not merely inert rocks drifting through space. They played a vital role in shaping Earth as we know it today. Through hydrogen isotope studies, we can trace the origins of water on our planet and better understand the contribution of these meteorites in delivering water and essential life-forming components. These cosmic couriers not only laid the foundation for the formation of oceans, but also triggered biological evolution, transforming a barren planet into a vibrant home for life. Looking back, every drop of water on Earth is not just a symbol of life, but also evidence of a journey spanning billions of years, from distant stars and meteorites to the green planet we call home. Can water alone create life? Or are additional secret ingredients from space needed to turn this miracle into reality? The answer lies in what meteorites and comets brought to Earth billions of years ago. Beyond delivering water, these celestial objects carried a treasure trove of organic molecules such as amino acids, sugars, and even prebiotic compounds. These are the raw materials essential for kickstarting life on the blue planet. In Earth's early days, violent impacts from meteorites and comets not only deposited water but also introduced organic molecules, the fundamental building blocks of life. Carbonaceous chondrite meteorites, considered time capsules from the early solar system, contained a wealth of organic compounds such as amino acids, the building blocks of proteins, carbon-based compounds, and precursor molecules for DNA and RNA. These collisions released not only water, but also these chemical bricks, laying the foundation for primitive life on Earth. As water from meteorites mixed into the primordial oceans, organic molecules began to disperse and interact within the energy-rich and dynamic environment of the planet. Sunlight, heat from deep-sea thermal vents, and volcanic activity all served as catalysts, driving complex chemical reactions. From simple molecules like amino acids, these reactions formed more intricate structures such as proteins and nucleic acids, two essential components of all living cells. This marked the first step in the long journey toward the emergence of life. According to scientists, the combination of water and organic compounds was the most critical factor for initiating life. Water not only shaped the formation of oceans, but also provided an ideal solvent environment for chemical reactions. Water dissolved organic compounds, enabling them to interact more easily and form complex molecules. Within this chemical soup, life might have begun to stir. The primordial oceans were not just reservoirs of water, but but also natural laboratories, where the first reactions leading to living structures took place. A clear modern-day parallel can be observed in mineral-rich geothermal pools, such as those in Yellowstone National Park. In these pools, the combination of water and organic substances from the surrounding environment generates complex chemical compounds. This serves as a miniature model reflecting what might have happened in Earth's early oceans. Similarly, organic molecules from meteorites participated in these processes on a planetary scale, laying the groundwork for the emergence and evolution of life. In fact, modern studies of meteorites like the Murchison meteorite, which fell to Earth in 1969, have revealed that these celestial objects contain dozens of naturally occurring amino acids. These molecules not only align with organic compounds found on Earth, but also provide direct evidence of meteorites' contributions to the origin of life. Additionally, analyses of comets like Halley's Comet have shown that the water and organic compounds within these bodies share significant similarities with those on Earth. This further supports the theory that meteorites and comets served as the first suppliers of life to the planet. Impacts from meteorites and comets were not just geological events. They were also biological milestones. They transformed Earth from a barren, arid planet into one rich in water and chemical diversity. The secret ingredients these meteorites delivered not only helped form oceans, but also activated the initial reactions that led to life. In conclusion, water from meteorites and comets was not merely a material resource, but a bridge between chemistry and biology. These celestial messengers brought the essential raw materials and created the conditions necessary for life to emerge. From a parched and scorching planet, Earth evolved into a home for life thanks to these water ambassadors from distant space. This reminds us that life is not the result of a miracle, but the outcome of billions of years of interaction between natural forces, from the cosmos to our planet. Great Lakes. The formation and evolution of the Great Lakes in North America. Have you ever wondered how 5 massive freshwater lakes, Superior, Michigan, Huron, Erie, and Ontario, that hold more than 20% of the world's surface freshwater, were formed through geological upheavals millions of years ago? The Great Lakes of North America were not naturally occurring bodies of water that appeared by chance. Rather, they are the results of complex geological processes spanning millions of years, beginning with tectonic shifts during the Cambrian period, approximately 500 million years ago. During the Cambrian period, Earth underwent significant geological changes. The enormous tectonic plates forming the planet's crust began shifting under pressure from the softer mantle layer beneath. This movement created massive cracks and valleys on the planet's surface, including the region that is now North America. These fractures not only shaped the geography, but also laid the groundwork for the initial geological structures where the Great Lakes would eventually form. At that time, the region was part of a massive supercontinent with continuous tectonic motion reshaping the Earth's surface and structure. The tectonic shifts of the Cambrian period did more than create cracks and valleys. They reshaped the entire topography of North America. Tectonic forces uplifted mountain ranges, depressed lowlands, and formed a network of deep valleys and basins where water would accumulate over millions of years. At this stage, these areas were still barren lands, devoid of water. Only later, with changes in climate and glacial activity, did water begin to fill these valleys, forming what we now know as the Great Lakes. A pivotal phase in the formation of the Great Lakes occurred during the Ice Age, which began around 2 million years ago and lasted until approximately 10,000 years ago. During this period, massive glaciers moved across North America. eroding soft rock layers and deepening the valleys that had been shaped during the Cambrian period. As the climate warmed and the glaciers melted, water from these ice flows accumulated in the valleys, creating large lakes. These glacial flows not only determined the depth and distinctive shapes of the lakes, but also provided their initial water supply. Consequently, the Great Lakes gradually emerged as the vast freshwater bodies we see today. A modern example illustrating how tectonic forces shape Earth's surface is the San Andreas Fault in California. This fault demonstrates how tectonic forces can cause significant transformations on the planet's surface, including the formation of large valleys and basins. Similarly, during the Cambrian period, powerful tectonic movements created a deep and expansive system of valleys in the North American region, where the Great Lakes later formed. These geological movements highlight nature's extraordinary ability to reshape the planet's surface. The Great Lakes are not only the result of tectonic activity, but also the product of a series of geological events spanning hundreds of millions of years, from arid valleys during the Cambrian period to the erosion and water accumulation during the Ice Age. Each step in this journey played a crucial role in transforming massive fractures and barren basins into the 5 largest freshwater lakes on Earth. Looking back, the formation of the Great Lakes was not a singular event, but the culmination of profound geological transformations over multiple epochs. The tectonic movements of the Cambrian period laid the foundation for the creation of valleys, while the Ice Age completed the process by filling them with fresh water. Today, the Great Lakes are not only a vital resource, but also a vivid testament to the power and complexity of geological processes that have shaped our planet. Did you know that massive glaciers were nature's sculptors, carving out the vast basins that now house the Great Lakes? During the Ice Age, which began around 2 million years ago, North America was blanketed by immense glaciers, thousands of meters thick. These glaciers were not static blocks of ice. Instead, they constantly moved under the force of gravity, demonstrating an unimaginable natural power. Their movement reshaped the landscape, deepening valleys and creating large basins that served as precursors to the Great Lakes we see today. As they moved, the glaciers dragged along rocks, soil, and other debris, functioning like a colossal natural sanding machine. This powerful abrasion eroded the hard rock beneath, deepening and widening pre-existing valleys formed millions of years earlier by tectonic activity. Over hundreds of thousands of years, this relentless grinding left an indelible mark on the surface of North America, creating massive basins that would later fill with water to form the Great Lakes. The erosive processes of glaciers not only altered the terrain, but also shaped the entire regional landscape. These massive ice flows acted as natural sculpting tools, constantly reshaping Earth's surface and creating the geographical features we can observe today. As the glaciers melted, they left behind clear evidence of their activity, such as deep basins, long grooves, and deposits of glacial sediments. These are valuable geological legacies, showcasing nature's incredible ability to reshape the planet. Imagine this process as similar to dragging a smooth stone across wet sand. As the stone moves, it leaves grooves and depressions in the sand, creating distinctive marks. In much the same way, the glaciers left behind vast and deep basins on North America's surface, which became the cradles of the modern Great Lakes. This process of abrasion and erosion not only created basins, but also shaped the rivers and water systems that later developed, playing a crucial role in forming the region's ecosystems. A concrete example of the power of glaciers to shape terrain can be seen in the glacial deposits still visible today. Scientists have discovered that the basin of Lake Superior, the largest of the Great Lakes, was formed through a combination of tectonic processes and glacial erosion. When the glaciers melted, water from the ice filled this deep basin, creating an enormous freshwater lake spanning over 82,000 square kilometers. This serves as a vivid testament to the role of glaciers in forming not only lakes, but also the characteristic landscape of North America. The Ice Age was not merely a cold chapter in Earth's history, but also a transformative era, during which nature harnessed the power of ice to recreate the planet's surface. The vast basins that now contain the Great Lakes are the result of hundreds of thousands of years of glacial erosion, abrasion, and carving. These are not just simple bodies of water, but natural marvels that preserve the remnants of a period of extraordinary geological upheaval. In retrospect, the formation of the Great Lakes was not solely the product of natural processes during the Cambrian period, but also the work of colossal glaciers during the Ice Age. These glaciers acted as great artists, sculpting and shaping the expansive basins that eventually became home to the world's largest freshwater lake system. The Great Lakes are not only vital sources of fresh water, but also enduring symbols of the extraordinary power and creativity of nature. What happens when billions of tons of ice melt? The answer lies in the formation of the planet's largest freshwater lakes, the Great Lakes of North America. At the end of the Ice Age, approximately 10,000 years ago, Earth entered a warming phase, melting the glaciers that had covered the region for millions of years. This melting process didn't occur rapidly, but stretched over thousands of years, with immense volumes of water slowly released from the ice, filling the basins carved by the glaciers long before. As these massive glaciers melted, they released enormous quantities of water, which filled the vast basins sculpted by the ice flows. This was not a singular event, but a prolonged series of processes where meltwater combined with mud, rocks, and sediments to form the unique landscapes of each lake. The melting not only brought water, but also reshaped the terrain, creating deep basins, shallows, and the surrounding lands. The Great Lakes, Superior, Michigan, Huron, Erie, and Ontario, all have distinct stories of formation, yet each stems from the wondrous interaction between ice and water. Lake Superior, the largest of the system, spans over 82,000 square kilometers, with depths exceeding 400 meters, standing as a clear testament to the power of glaciers in shaping landscapes. Similarly, other lakes such as Michigan and Huron are not merely reservoirs, but the results of erosion and sedimentation, with each layer of silt and deposit recounting their formation's history. Beyond delivering water, the melting glaciers also deposited mineral-rich sediments, crucial for shaping the area's unique ecosystems. These layers of sediment, accumulated over thousands of years, became the foundation for the development of aquatic life, as well as the flora and fauna around the lakes. This has transformed the Great Lakes into not only the largest source of fresh water in the world, but also a rich and diverse ecosystem supporting millions of species. A modern example illustrating this process is the melting of glaciers in Greenland. The massive meltwaters there not only flow into the sea, but also collect to form new lakes, reminiscent of how the Great Lakes of North America were formed. This phenomenon highlights the power of glacial meltwater to reshape landscapes, creating new water bodies with the potential for ecological development. In Earth's history, the melting of glaciers at the end of the Ice Age not only marked the end of a frigid era, but also heralded a new chapter. The enormous volumes of meltwater created one of nature's greatest wonders, the Great Lakes. These lakes are more than just bodies of water. They are natural mirrors reflecting geological history, invaluable resources, and a source of human inspiration and exploration. The formation of the Great Lakes of North America stands as a testament to nature's power to recreate and reshape the planet. This process was not just the conclusion of the Ice Age, but also the beginning of the world's largest freshwater system. The Great Lakes serve not only as vital sources of water, but also as symbols of life, transformation, and Earth's boundless capacity for renewal. Looking back, each drop of water in these lakes holds not just thousands of years of history, but also a reminder of the strength and wonder of nature. The impact of ice ages and the phenomenon of ice melting. Did you know that thousands of meters of ice once blanketed North America? And it was this massive weight of ice that sculpted the region's landscape and created the magnificent Great Lakes we see today? The Ice Ages, marked by the emergence of immense glaciers slowly moving across the Earth's surface, played a pivotal role in altering geological structures and shaping the region's terrain. These transformations not only left deep imprints on the land, but also laid the foundation for the existence of the Great Lakes system, one of the planet's most extraordinary natural wonders. During the Ice Ages, North America experienced extended periods of intense cold lasting tens of thousands of years, with massive ice sheets covering nearly the entire region. These ice sheets, thousands of meters thick, exerted tremendous pressure on the Earth's surface beneath them. This pressure not only altered geological structures, but also reshaped the region's terrain. Some areas were compressed under the ice's weight, causing them to sink, while others were pushed upward, creating unique topographical features. This phenomenon, known as glacial sculpting, played a central role in the formation of the Great Lakes. The slow movement of glaciers had a profound impact on the landscape. As these massive ice sheets advanced across the Earth's surface, they acted as giant natural grinders, eroding the bedrock beneath. This process of abrasion wore down hard rock layers, carving out long grooves and deep valleys. These areas, after the ice melted, became large basins, eventually filling with water to form the Great Lakes. Moreover, the moving ice left behind distinctive geological features such as cracks, crevices, and lowlands, all contributing to the unique structure of the Great Lakes system. One striking aspect of glacial influence is how the ice specifically shaped each lake. Lake Superior, the largest in the system, was formed from a deep basin carved out by glacial movement. Similarly, Lakes Michigan and Huron were created from expansive valleys where glaciers eroded and deepened the rocky surface. These geological characteristics vividly demonstrate the power of glaciers in sculpting landscapes, transforming the region from arid terrain into the largest freshwater lake system on the planet. This process of glacial sculpting isn't just a phenomenon of North America's past. It is still occurring in areas with active glaciers today. Greenland, for instance, provides a modern example where massive glaciers continue to move, eroding the underlying rock and creating deep valleys and glacial rivers. These ongoing changes offer a tangible glimpse into how ice ages shaped North America and demonstrate the enduring power of glaciers to reshape the Earth's surface. The ice ages not only left physical imprints, but also contributed to the region's life and ecosystems. The basins carved out by glaciers, once filled with meltwater, became the world's largest source of fresh water, providing habitats for millions of species and fulfilling human needs. The areas surrounding the Great Lakes today are not only economic and social hubs, but also symbols of the harmony between nature and humanity. Looking back, the Ice Ages were not merely cold periods in the Earth's history, but transformative epochs that defined North America's terrain. The presence and movement of glaciers not only created unique geological features, but also laid the groundwork for the formation of the Great Lakes system, a vital natural wonder of the planet. These freshwater lakes are more than just legacies of the Ice Ages. They are enduring reminders of nature's extraordinary power and its capacity for continuous transformation. What happens when billions of tons of ice melt? When billions of tons of ice melt, it doesn't just result in the formation of vast freshwater lakes. It also gives rise to unique ecosystems that play a crucial role in fostering biodiversity within the Great Lakes. At the end of the Ice Age, approximately 10,000 years ago, as the Earth's climate warmed, massive glaciers began to melt, releasing immense quantities of water into the deep basins previously carved out by the glaciers. However, water wasn't the only thing released. Strong meltwater flows also carried soil, silt, and sediments from the glaciers and surrounding land, setting the stage for the nascent ecosystems of the Great Lakes. These meltwater streams not only filled the basins, but also carried vast amounts of sediment, including fine soil, rock fragments, and minerals. These materials accumulated along the lake beds and shores, forming a nutrient-rich foundation. This sediment layer became a vital source of nutrients, laying the groundwork for early ecosystems to develop in and around the Great Lakes. This phase was essential in establishing food chains, starting with microorganisms and small aquatic plants, progressing to fish and larger aquatic species, and eventually supporting terrestrial wildlife. The initial ecosystems of the Great Lakes were built upon the abundance of deposited sediments. Nutrients such as nitrogen, phosphorus, and potassium, carried by the glacial meltwater, provided ideal conditions for the growth of aquatic plants like algae and seaweed. These plants not only produced oxygen, but also served as food for small animals like crustaceans and zooplankton. Over time, fish, birds, and larger animals appeared, completing the food web within the ecosystem. Through this process, the Great Lakes quickly evolved into diverse habitats that supported millions of different species. Lake Erie, one of the 5 Great Lakes, serves as a prime example of how glacial meltwater and sediment created thriving ecosystems. As meltwater flowed into the basin, dense layers of silt and sediment accumulated on the lakebed, providing a rich nutrient source for plants and animals. Studies reveal that these sediments were key drivers of the growth of fish populations and aquatic life in Lake Erie, transforming it into one of the world's most productive freshwater environments. A modern parallel can be observed in glacial meltwater lakes in Alaska, where nutrient-rich sediments from melting ice create favorable conditions for salmon and other aquatic species to thrive. In addition to providing habitats, sediment also shaped the geographical features of the Great Lakes. Sandbars, coastal landforms, and small islands are all products of thousands of years of sediment deposition. These features not only enhance the diversity of the landscape, but also play a vital role in protecting the lake shores from erosion, maintaining the stability of ecosystems in the surrounding areas. The melting of glaciers at the end of the Ice Age not only created vast lake basins, but also initiated a series of complex ecological events, transforming the Great Lakes into the rich and diverse ecosystems they are today. The meltwater and sediment carried by the ice not only provided resources for flora and fauna, but also shaped the landscapes and environments in the region. Thanks to their natural wealth and ecosystems, the Great Lakes have become one of the most significant natural wonders in the world. Reflecting on this process, the melting of glaciers was not just a geological event, but also an ecological turning point. Meltwater streams carrying sediment from the ice created a unique ecosystem, ranging from microscopic organisms to large animals, all thriving in and around the Great Lakes. This story is not just about the formation of lakes, but also about how nature regenerates and fosters life under the most challenging conditions. The Great Lakes, with their biodiversity and vibrant ecosystems, are a priceless legacy of this process. Have you ever thought that the Great Lakes continuously change their shape and water levels, even millions of years after they were formed. In fact, the evolution of the Great Lakes is ongoing, influenced by natural phenomena such as geological rebound and climate change. After each ice age, these factors not only reshape the size and depth of the lakes, but also significantly impact the surrounding ecosystems, transforming them into ever-changing natural wonders. When massive glaciers melted at the end of each ice age, they left behind significant geological changes. One of the most critical phenomena is isostatic rebound. Previously, the immense weight of glaciers compressed the Earth's surface, causing some areas to sink. As the ice melted, this pressure disappeared, and the land began to slowly rise, while other regions might have subsided due to the redistribution of sediments. This rebound process does not occur instantly, but stretches over thousands to millions of years, leading to significant changes in the shape and water levels of the lakes. Many areas were uplifted, reducing lake depths, while other regions sank, creating new lake branches or expanding existing basins. Beyond geological rebound, climate also plays a crucial role in regulating the water levels and shapes of the Great Lakes. Global warming after each ice age increased temperatures, accelerating water evaporation and causing lake levels to drop. Conversely, colder climate phases with higher precipitation added more water to the lakes, increasing their size and depth. These climatic fluctuations occurred not only in the past, but continue to affect the Great Lakes today, especially in the context of modern climate change. Rising global temperatures have accelerated evaporation rates while reducing water replenishment from snowmelt and rainfall, leading to significant changes in the lake's water levels. A typical example of these changes can be seen in Lake Huron, one of the 5 Great Lakes. The geological history of Lake Huron records significant water level fluctuations, ranging from prolonged droughts that left the lakebed dry to severe flooding that inundated coastal areas. These changes were driven not only by geological rebound, but also by climatic variations over thousands of years. Scientists have noted that, in certain periods, geological rebound caused parts of the lakebed to rise, significantly reducing the lake's surface area. Conversely, during wetter climate periods, substantial water replenishment caused water levels to surge, expanding the lake's range. Beyond Lake Huron, the entire Great Lakes system has experienced similar transformations. The original file discusses how geological rebound and climate change have altered the lake's depth and shape, gradually stabilizing them over time. However, this stability is only relative, as geological and climatic factors continue to influence the Great Lakes, keeping them in a state of constant change. This clearly demonstrates that these lakes are not static entities, but dynamic systems reflecting the ongoing interplay of natural forces. Overall, the formation and development of the Great Lakes are not singular events, but a series of changes spanning millions of years. From the effects of geological rebound to climate change, each factor has contributed to shaping the Great Lakes as we see them today. Even in modern times, the water levels and shapes of these lakes continue to evolve, posing significant challenges for ecosystems and communities reliant on these water sources. In conclusion, the evolution of the Great Lakes vividly illustrates the close relationship between geology and climate. Natural changes following each ice age not only redefined the lake's landscapes, but also laid the foundation for the development of unique ecosystems in the region. The Great Lakes are not merely vast water reservoirs, but also an ever-evolving story, showcasing nature's power and continuous transformation. Even today, they continue to change, reminding us that nature is always a dynamic system with impacts and consequences that endure over time. The role of the Great Lakes in regional ecosystems and climate. Did you know that the Great Lakes in North America alone hold nearly 20% of the world's total surface fresh water? With a total surface area of over 244,000 square kilometers and a volume of approximately 23,000 cubic kilometers, the Great Lakes system is not just a natural wonder, but also a massive freshwater reservoir serving millions of organisms and humans. This vital role makes the Great Lakes an essential part of the regional ecosystem and economy, as well as the largest surface freshwater source on the planet. The water in the Great Lakes not only sustains life, but also underpins economic and social development. Millions of people living around the Great Lakes, from Canada to the United States, depend on this water source for daily needs, such as drinking, cooking, and sanitation. Major cities like Chicago, Toronto, Cleveland, and Detroit draw water from the Great Lakes to supply their residents. Furthermore, the Great Lakes serve as a crucial water source for agriculture and industry in the region. Irrigation systems, farming, and livestock in the U.S. Midwest consume large amounts of water from these lakes, ensuring productivity and food supply for millions of people. Industry also heavily relies on water from the Great Lakes. Manufacturing plants, particularly in the automotive and steel sectors, use water from the lakes for cooling industrial systems and regulating temperatures during production processes. Water from the Great Lakes is also used to operate power plants, contributing to the region's energy supply. The network of canals and ports connecting the lakes not only supports waterway transportation, but also boosts trade, making the Great Lakes a key economic hub of North America. The Great Lakes system is not only significant for humans, but also serves as a critical habitat for millions of species. These lakes are home to many rare fish species, such as salmon and walleye, along with hundreds of other aquatic creatures. The wetlands surrounding the lakes also provide ideal breeding grounds for migratory birds and other flora and fauna. The role of the Great Lakes extends beyond providing water. They are an essential part of the global ecosystem, supporting natural balance and biodiversity conservation. A clear example of the value of the Great Lakes is Lake Michigan, which supplies water to over 10 million people in the U.S. and Canada. Beyond being a source of domestic water, Lake Michigan significantly contributes to the manufacturing industry in the U.S. Midwest, one of the most important production centers in North America's economy. Similarly, in Vietnam, the role of Dao Tieng Lake in providing water for Ho Chi Minh City serves as a relatable example of the importance of large lakes. This underscores that lakes, wherever they are, play a crucial role in sustaining life and fostering economic development. The Great Lakes are not just freshwater reservoirs, but symbols of the connection between nature and humanity. With over 20% of the world's surface freshwater, they sustain millions of organisms and support the regional economy. However, the Great Lakes are also facing numerous challenges, such as pollution, climate change, and overexploitation, requiring conservation and sustainable management efforts from both the U.S. and Canada. The survival and health of the Great Lakes are not just regional issues, but have a direct impact on ecosystems and freshwater resources worldwide. In retrospect, the Great Lakes are clear evidence of the importance of freshwater in sustaining life and driving economic development. They not only provide a precious water source, but also form the foundation for the sustainable development of the North American region. Amid climate change and human pressures, protecting the Great Lakes is not only a local responsibility, but a global mission to ensure this vital water resource and ecosystem persist for future generations. Have you ever wondered why the weather around the Great Lakes region is more pleasant, even during freezing winters or sweltering summers? The answer lies in the role of the Great Lakes as natural climate regulators. These massive bodies of water are not only a source of fresh water, but also have the ability to regulate the regional climate, mitigating extreme weather conditions and providing significant benefits to both the environment and humans. Water in the Great Lakes has a unique characteristic: the ability to absorb and release heat over time. In summer, when the surrounding air heats up, the lakes absorb a large amount of heat from the environment, cooling the air and creating a natural cooling effect. Conversely, in winter, the lakes release the heat accumulated during the summer, warming the surrounding air. This process occurs gradually but continuously, helping maintain more stable temperatures in areas near the lakes. This is why cities near the Great Lakes, such as Chicago, Toronto, and Cleveland, often experience milder weather compared to other inland areas of North America. The climate-regulating effect of the Great Lakes is not limited to warming in winter or cooling in summer. They also influence rainfall and other weather phenomena in the region. The Great Lakes act as a major source of water vapor, providing moisture to the atmosphere. This helps sustain consistent rainfall, especially during dry seasons. Additionally, the lake effect snow phenomenon, where increased snowfall occurs near the lakes due to evaporating water vapor, is a unique feature of the Great Lakes climate, bringing intriguing and sometimes beneficial changes to the local ecosystem. Thanks to their climate-regulating abilities, the Great Lakes provide immense benefits to agriculture and human life. Crops in areas near the lakes often thrive due to the stable climate and adequate rainfall. Specifically, in southern Ontario, the warming effect of the Great Lakes protects crops from unusual autumn frosts, extending the harvest season and boosting agricultural yields. Similarly, in the U.S. Midwest, farms near the lakes take advantage of the moderate climate to grow crops such as corn, wheat, and fruits, meeting the food needs of millions of people. This climate-regulating capacity not only provides ideal living conditions for humans, but also maintains the stability of local ecosystems. Flora and fauna in and around the Great Lakes benefit from a less volatile temperature environment and higher humidity, preserving biodiversity. Fish species in the lakes, such as salmon and walleye, also thrive due to the stability of water temperatures, which are crucial for reproduction and growth. A clear example of the climate-regulating role of the Great Lakes is how they protect crops from harsh weather. Lake Ontario, for instance, has a significant impact on the agricultural region of southern Ontario, enabling the mass production of fruits and vegetables thanks to the mild climate it provides. Similarly, in Vietnam, large hydropower reservoirs like Hoa Binh Lake contribute to regional climate regulation, reducing temperatures during summer months and providing consistent moisture to the surrounding environment. These examples highlight the importance of large lakes in creating favorable and sustainable living conditions for both humans and wildlife. The climate-regulating function of the Great Lakes not only offers practical benefits for daily life, but also contributes to the sustainable development of the region. With the ability to stabilize temperatures, provide moisture, and influence rainfall, these lakes play an irreplaceable role in maintaining natural balance and supporting economic, agricultural, and industrial activities. In summary, the Great Lakes are not just vast freshwater reservoirs, but an essential part of the natural climate regulation system. They provide benefits far beyond expectations, from alleviating harsh weather to supporting agricultural activities and protecting ecosystems. This role is not only vital for the past and present, but will remain a key factor in ensuring a sustainable future for the region and the world. Did you know that the Great Lakes are not just massive bodies of water, but also living oases, hosting thousands of species and serving as hubs for regional economic activities? The ecosystem of the Great Lakes is incredibly rich, providing life to countless plant and animal species, while playing a vital role in commerce, agriculture, and tourism. These lakes are not just reservoirs of fresh water, but are an indispensable part of both the ecosystem and the economy of North America. With over 170 species of fish, hundreds of migratory bird species, and many unique aquatic organisms, the Great Lakes are among the most biodiverse freshwater ecosystems in the world. Fish such as salmon, walleye, perch, and cod are not only important food sources, but also the focus of commercial fishing industries and recreational activities like sport fishing. The wetlands surrounding the lakes are home to numerous rare bird species and wildlife, from bald eagles to sandhill cranes. The Great Lakes are not just cradles of life, but also sources of inspiration and exploration for researchers, photographers, and nature enthusiasts. Beyond their ecological role, the Great Lakes are key drivers of economic activity in North America. With major ports like Duluth on Lake Superior and Detroit on Lake Huron, the Great Lakes system is a vital part of international trade networks, connecting North America to other parts of the world. Goods such as steel, grain, and lumber are transported through these waterways, contributing to the region's economic development. Lakeside cities are not only commercial hubs, but also centers for thriving industries, from food processing to heavy industrial manufacturing. Agriculture greatly benefits from the Great Lakes as well. The lakes provide essential freshwater for irrigation systems, boosting crop yields and ensuring food security for millions of people. The lands near the lakes, with their mild climate and abundant water, are ideal for cultivating crops like corn, soybeans, and fruits. The stability of ecosystems around the Great Lakes not only supports agricultural production, but also fosters the growth of local communities. Tourism is another significant economic sector built around the Great Lakes. With breathtaking natural scenery and diverse ecosystems, the lakes attract millions of visitors each year. Activities such as boating, fishing, swimming, and picnicking not only offer unforgettable experiences for tourists, but also generate substantial revenue for the tourism industry. Lake Erie, with its rich ecosystem, is a popular destination for water-related recreational activities, from sport fishing to visiting nature reserves. Similarly, Lake Superior, known for its pristine beauty, is ideal for nature exploration and camping trips. A compelling example of the diversity and value of the Great Lakes is Lake Erie. Its ecosystem not only provides significant benefits through the fishing industry, but also draws thousands of visitors annually. From the shimmering surface of the Great Lakes, let us look up to the sky, where the atmosphere, Earth's invisible protective blanket, has shaped life in miraculous ways. But how was this layer formed? And what makes it a crucial element for life on our planet? Let us uncover the story of the vast expanse right above us, our atmosphere, the formation of Earth's atmosphere. Through different stages, have you ever thought that Earth's atmosphere was once nothing like the fresh air we breathe today? In fact, the earliest stage of Earth's atmospheric history, known as the primordial atmosphere, was entirely different. This atmosphere primarily consisted of hydrogen and helium, the two lightest elements in the universe, forming a thin envelope around the young planet. However, the primordial atmosphere did not last long, and its disappearance marked the first step in the formation of the complex atmosphere we have today. Around 4.5 billion years ago, Earth formed from the dust and gas cloud that created the solar system. During this period, the planet was still hot and lacked the stable structure it has now. Light elements like hydrogen and helium, remnants of the primordial nebula, enveloped the young Earth, creating its initial atmosphere. This atmospheric layer acted as a thin membrane surrounding the planet, but it was highly vulnerable to external forces. At that time, Earth's gravitational pull was not strong enough to retain light elements like hydrogen and helium. These gases, due to their low mass, were easily able to escape the planet's gravitational pull. This process was exacerbated by the impact of solar winds. Solar winds are streams of high-energy particles emitted from the sun's surface at great speed. When these particles collided with Earth's atmosphere, they exerted intense pressure, driving hydrogen and helium out of the atmosphere and dispersing them into space. As a result, Earth's primordial atmosphere was quickly lost. In a relatively short span on the planet's geological timescale, Earth became barren, lacking a protective atmospheric layer. At this stage, the planet resembled a desolate surface of molten lava, devoid of water, air, or any signs of life. This was a tumultuous period, as Earth faced significant challenges from the cosmos, laying the groundwork for the subsequent stages of atmospheric development. The loss of Earth's primordial atmosphere also provides insights into the evolution of other planets in the solar system. For example, Jupiter, with its extremely strong gravitational pull, has retained gases like hydrogen and helium in its atmosphere for billions of years. In contrast, Mars, with weaker gravity, could not maintain a thick atmosphere when exposed to solar winds. Today, Mars has a thin atmosphere, barely capable of supporting life. These comparisons highlight the critical roles of gravity and solar winds in shaping the atmospheres of planets. Although Earth's primordial atmosphere did not last long, its disappearance was a pivotal moment in the planet's history. As this first layer was swept away, Earth gradually transitioned to the formation of its second atmosphere. This process involved volcanic eruptions that released gases from the Earth's interior, creating a new atmosphere rich in carbon dioxide, water vapor, and nitrogen. This became the foundation for the current atmosphere, which supports life and protects the planet from cosmic impacts. Looking back, the primordial atmosphere stage is not just a chapter in Earth's geological history, but also a testament to the complex interactions between cosmic and planetary forces. Although it was short-lived, it paved the way for the planet's subsequent development. The loss of hydrogen and helium from the primordial atmosphere reminds us of the fragility of young planets in the face of powerful cosmic forces. It also marked the first step in Earth's journey from a barren planet to the thriving home for life that we know today. Did you know that volcanic eruptions were the primary source of the second atmosphere, paving the way for the emergence of Earth's oceans? After the primordial atmosphere was swept into space, Earth entered a completely new phase in the development of its atmosphere. This stage was marked by the formation of the second atmosphere, a significant turning point in the planet's history. The origin of this atmosphere was not external, but came from within Earth itself, through massive volcanic eruptions. Around 4 billion years ago, Earth was still a scorching planet, with intense volcanic activity occurring everywhere. These eruptions not only expelled lava, but also released large amounts of gases into the surrounding space. Carbon dioxide, CO2, water vapor, H2O, methane, CH4, and ammonia, NH3, were the primary components emitted from vents and volcanoes. These gases gradually accumulated, forming the second atmosphere that enveloped the planet, signaling a new era with completely different natural conditions. Water vapor, among the gases released, played a particularly crucial role in Earth's development. As the planet gradually cooled, the water vapor in the atmosphere began to condense into tiny droplets, creating prolonged rainstorms that lasted millions of years. These rains not only reduced surface temperatures, but also filled the depressions and deep basins formed by geological activity, leading to the emergence of the first oceans. These bodies of water were not merely reservoirs, but a crucial stepping stone for the development of life on the planet. In addition to water vapor, carbon dioxide was also indispensable in the second atmosphere. Although CO2 is now regarded as a primary contributor to climate change, It was an essential factor in stabilizing Earth's temperature during its early stages. Carbon dioxide created a greenhouse effect, trapping heat within the atmosphere and preventing the planet from becoming too cold for liquid water to exist. Without a CO2-rich atmosphere, Earth could have been entirely frozen, making it impossible for oceans to form and life to begin. Methane and ammonia, though present in smaller amounts, also played vital roles in shaping the chemical properties of the second atmosphere. Together with water vapor and CO2, these gases created an environment rich in chemical energy, providing the necessary ingredients for the first chemical reactions, a precursor to the development of organic compounds and early life. A clear illustration of the role of volcanoes in forming the atmosphere can be seen in modern volcanic activity. For example, Hawaii's Kilauea volcano continuously emits CO2, water vapor, and other gases, similar to how ancient volcanoes operated billions of years ago. These modern eruptions serve as a small-scale model, helping us better understand the processes involved in the formation of Earth's second atmosphere. The emergence of the second atmosphere was a critical milestone in the planet's history. It not only provided the necessary gases for the formation of oceans, but also created a stable environment suitable for life to arise. Gases such as CO2 and methane produced a greenhouse effect, maintaining surface temperatures warm enough for liquid water, while water vapor and ammonia contributed to the chemical conditions required for prebiotic reactions. Looking back, the second atmosphere was not just a gaseous layer enveloping the planet, but a decisive factor in transforming Earth from a molten mass into a planet with water and the potential to support life. Volcanic eruptions, though seemingly chaotic and destructive, were crucial forces driving the planet closer to the state we know today. They marked the origin of the oceans, the cradle of life, and represented an indispensable step in Earth's long journey of formation. How did Earth transform from a planet devoid of oxygen to a world teeming with life, thanks to tiny organisms like cyanobacteria? The answer lies in a revolutionary event spanning billions of years, known as the Great Oxidation Event. This marked the final stage in the formation of Earth's atmosphere. As an atmosphere rich in CO2 and oxygen deficient transitioned into an oxygen-rich environment, the foundation for the complex life forms we see today. Around 2.5 billion years ago, Earth's atmosphere was primarily composed of CO2, methane, and other gases unsuitable for supporting complex life. Everything began to change with the emergence of cyanobacteria, tiny organisms living in Earth's primordial oceans. Through photosynthesis, cyanobacteria used sunlight to convert CO2 and water into energy, releasing oxygen as a byproduct. For the first time, oxygen was produced in significant amounts, marking a crucial turning point in the planet's history. Initially, oxygen did not accumulate directly in the atmosphere. Instead, it reacted with dissolved iron in seawater, forming iron oxide deposits that settled on the ocean floor as banded iron formations. This process continued for millions of years until the iron in the oceans was depleted. Only then did oxygen begin to build up in the atmosphere. This gradual rise in oxygen culminated in the Great Oxidation Event, a period when atmospheric oxygen levels increased significantly, approximately 2.3 billion years ago. This was not merely a chemical shift, but a fundamental transformation that shaped Earth's future. The Great Oxidation Event not only altered the atmosphere, but also profoundly impacted ecosystems. Anaerobic organisms, those that do not use oxygen, which had previously dominated, faced a massive decline as they could not adapt to the increasing oxygen levels. Conversely, oxygen created ideal conditions for the emergence of aerobic organisms, those that use oxygen to metabolize energy. paving the way for the evolution of complex animals. Oxygen also played a critical role in forming the ozone layer, which shielded the planet's surface from harmful ultraviolet radiation, creating safer conditions for life to thrive on land. Examples from planetary history highlight the significance of the Great Oxidation Event. A modern analogy is the role of tropical rainforests, like the Amazon, in producing oxygen and maintaining atmospheric balance. Scientists also compare this process to smaller ecosystems, such as photosynthetic organisms in ponds, where oxygen is released to sustain aquatic plant and animal life. These examples help us better understand the importance of cyanobacteria in shaping Earth's atmosphere billions of years ago. The Great Oxidation Event also had geological implications for the planet. The iron oxide deposits that precipitated in the primordial oceans, a result of the reaction between oxygen and iron, have become essential resources today, mined for steel production and various other materials. This demonstrates the lasting economic and technological impacts of atmospheric changes from Earth's distant past. By the end of this phase, Earth's atmosphere had reached the state we recognize today, with oxygen constituting about 21%. This remarkable achievement of nature was driven by tiny organisms like cyanobacteria that completely transformed the planet's environment. From an atmosphere dominated by CO2, methane, and ammonia, Earth evolved into a planet capable of supporting complex life, with oxygen as a critical component in all biological processes. Looking back, this transformation is a testament to the intricate relationship between biological and chemical factors on Earth. The Great Oxidation Event not only created a conducive environment for life, but also shaped the structure of the atmosphere and current ecosystems. From the smallest organisms, Earth gradually evolved into a planet full of life, ushering in an era of complex organisms and, ultimately, humanity. The role of oxygen in life and evolution. Did you know that with just one molecule of oxygen, cells in your body can produce millions of units of energy necessary to sustain life? Oxygen is not merely a simple chemical element, but the foundation of modern life, playing an indispensable role in the respiration of most organisms on Earth. Thanks to oxygen, living beings can metabolize energy more efficiently, enabling them to sustain complex life activities and thrive in diverse ecosystems. Respiration is the process of converting energy from food, where oxygen plays a central role. When oxygen combines with glucose, it generates adenosine triphosphate, ATP, the usable form of energy for cells. This process, known as aerobic respiration, occurs in most living organisms, from bacteria to humans. ATP is the energy currency of the body, fueling all vital activities, from muscle contraction and nerve signal transmission to cell repair. Compared to organisms that do not use oxygen, such as those relying on fermentation, aerobic organisms can produce significantly more energy. This allows them to grow larger, become more complex, and perform advanced biological functions. Not only animals, but also plants and microorganisms rely on oxygen to sustain life. While plants produce oxygen through photosynthesis, they also use oxygen during cellular respiration, particularly at night, when photosynthesis cannot occur. This process helps plants convert stored energy from glucose to grow and maintain their functions. Similarly, aerobic microorganisms, including bacteria and fungi, require oxygen to carry out essential functions such as growth, reproduction, and organic matter decomposition. Oxygen not only provides energy for microorganisms, but also promotes nutrient recycling in ecosystems, maintaining balanced and stable environments. The critical role of oxygen in modern life is vividly illustrated through the human respiratory system. Humans inhale approximately 21% oxygen in the air, and even a slight deficiency can lead to severe consequences. Oxygen not only powers the body, but also plays a vital role in maintaining the functions of organs, particularly the brain. When the brain is deprived of oxygen for just a few minutes, nerve cells sustain irreversible damage, leading to impaired function or death. This demonstrates the life or death dependence of humans on oxygen. In evolutionary history, oxygen was a decisive factor in the development of the first multicellular organisms on Earth. Around 2.5 billion years ago, the Great Oxidation Event transformed the atmospheric composition from CO2-rich to oxygen-rich. This not only created ideal conditions for aerobic organisms, but also drove the evolution of more complex species. Oxygen-rich oceans supported the growth of large marine organisms, while the ozone layer, formed from oxygen, shielded the planet's surface from ultraviolet radiation, paving the way for terrestrial life. A relatable example is the role of oxygen in aquatic ecosystems. Fish and other aquatic organisms depend on dissolved oxygen in water for respiration. When oxygen levels drop, such as during eutrophication events, these organisms suffer mass die-offs, disrupting ecological balance. This highlights that oxygen is crucial not only within organisms, but also in maintaining the stability of living environments. Overall, oxygen is an indispensable element of modern life. From providing efficient energy to organisms, supporting ecosystem functions, to protecting the planet from harmful radiation, oxygen is the key to the development of all life forms on Earth. Its presence in the atmosphere is not only a natural milestone, but also the foundation for the existence and evolution of humanity. How could a small change in oxygen levels trigger the greatest biological revolution in Earth's history? The answer lies in the Cambrian period, around 540 million years ago, when our planet witnessed an unprecedented biological explosion. This was a time when a vast array of multicellular animals appeared at a rapid pace, marking a remarkable leap in evolutionary history. The key driver of this event was the increase in oxygen levels in the atmosphere and oceans, creating the ideal environment for complex life to flourish. Before the Cambrian period, Earth was primarily home to microorganisms and unicellular organisms living in low-oxygen environments. This limitation allowed organisms to grow only to small sizes with simple structures. When oxygen levels in the atmosphere and seawater rose significantly, everything began to change. Oxygen served as a vital energy source, enabling more complex organisms to emerge. This not only allowed them to grow larger, but also supported the development of more intricate body systems, such as circulatory, nervous, and skeletal systems. An oxygen-rich environment paved the way for the evolution of the first vertebrates, along with other animals with complex structures. These organisms utilized oxygen for aerobic respiration, a process that produces energy far more efficiently than earlier metabolic methods. As a result, they gained the ability to move more flexibly, hunt prey more effectively, and defend themselves against predators. This formed the foundation for the complex food chains and diverse ecosystems we observe today. Notably, the increase in oxygen levels was not merely a result of natural environmental changes, but also an outcome of interactions between organisms and their surroundings. Photosynthetic organisms, such as cyanobacteria and algae, produced large quantities of oxygen through photosynthesis. This oxygen, in turn, spurred the evolution of new organisms, creating a positive feedback loop. This interaction clearly demonstrates how organisms and their environments can co-evolve and drive change together. One of the most prominent examples of the Cambrian biological explosion is the emergence of trilobites, one of the first animals with a complex nervous system and an exoskeleton. Trilobites became a symbol of this era, showcasing evolutionary advancements compared to the simpler organisms that preceded them. Besides trilobites, numerous other animals appeared during this period, ranging from small crustaceans to creatures with body structures resembling modern animals. Another clear example can be observed in today's deep-sea regions, where low oxygen levels restrict life to simpler forms. In these areas, only tiny organisms like bacteria or simple crustaceans can survive. This illustrates that high oxygen levels are a prerequisite for the development of complex organisms. The events of the Cambrian period underscore oxygen's role in shaping life on Earth. Thanks to an oxygen-rich environment, organisms not only grew in size and complexity, but also achieved physiological breakthroughs, such as efficient digestion, blood circulation, and rapid metabolism. These adaptations allowed them to dominate ecosystems and drive biodiversity. The rise in oxygen levels during the Cambrian period was not just a chemical shift in the environment, but a powerful catalyst for biological evolution. It transformed a planet of simple life forms into the rich, diverse world we see today. Oxygen not only enabled complex organisms to exist, but also laid the foundation for the development of entire ecosystems from oceans to land. Looking back, the Cambrian biological explosion is a testament to the extraordinary power of a small but vital molecule, oxygen, in reshaping the history of life on our planet. Did you know that a single molecule of oxygen not only sustains life, but also transforms into a global protective shield, shielding Earth from harmful UV rays? When oxygen began to accumulate in Earth's atmosphere around 2.5 billion years ago, a small portion of it started converting into ozone, O3, through photochemical reactions. The ozone layer, formed in the stratosphere, became a crucial natural shield, absorbing most of the sun's ultraviolet, UV radiation. This marked an essential turning point, ensuring the survival of life on the planet by protecting it from the harmful effects of UV rays. Ultraviolet radiation can cause severe damage to the DNA of organisms, leading to genetic mutations, diseases, and even extinction with prolonged exposure. Before the ozone layer formed, organisms on Earth lived primarily underwater. Water acted as a natural barrier, shielding them from UV radiation. This explains why early life on the planet existed only in the oceans. However, once the ozone layer stabilized and began shielding Earth's surface, life could venture out of the oceans, ushering in a new era for terrestrial organisms. The formation of the ozone layer began when oxygen molecules, O2, in the atmosphere absorbed energy from UV light, splitting into individual oxygen atoms. These atoms then combined with other O2 molecules to form ozone, O3. The ozone layer not only absorbed UVB and UVC, the most harmful forms of radiation, but also played a role in regulating the temperature of the stratosphere, contributing to a more stable climate on the planet. The role of the ozone layer is evident in evolutionary history. During the Devonian period, around 400 million years ago, when the ozone layer had stabilized, plants and animals began colonizing land. Higher plants, such as giant ferns, thrived, providing food and habitats for early terrestrial animals. Amphibians, the ancestors of modern vertebrates, began transitioning from water to land. Without the ozone layer's protection from UV rays, these critical milestones in evolution could not have occurred. A modern example of the ozone layer's importance can be seen in the phenomenon of the ozone hole over Antarctica. Due to the impact of chemicals such as chlorofluorocarbons, CFCs, the ozone layer in this region has been severely depleted, resulting in higher levels of UV radiation reaching the ground. This not only harms ecosystems but also threatens human health, with increased rates of skin cancer and cataracts in affected areas. Antarctic marine ecosystems, particularly plankton, the foundation of the food chain, have also suffered significant disruptions, affecting ecological balance. The ozone layer is also vital for maintaining biodiversity on Earth. It protects crops from UV damage, ensuring agricultural productivity and food security. Additionally, the ozone layer helps sustain marine ecosystems, where plankton play a critical role in absorbing CO2 and producing oxygen, two essential processes for maintaining global atmospheric balance. In summary, the ozone layer is a clear testament to the comprehensive role of oxygen in sustaining and protecting life. Thanks to the ozone layer, Earth is not only a habitable planet, but also a safe haven for life to evolve and thrive on land. It is one of the most crucial factors that has transformed Earth into a home for diverse and abundant life, enabling organisms to flourish for billions of years. The impact of greenhouse gases and current climate change. Did you know that gases like CO2 and CH4 not only warm the Earth, but are also pushing our planet into an unprecedented climate crisis? Greenhouse gases, including carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O, play a crucial role in maintaining Earth's temperature at levels suitable for life. They act as a natural blanket, absorbing energy from sunlight and trapping heat in the atmosphere, preventing it from escaping into space too quickly. Without greenhouse gases, the Earth's average temperature would be around -18 degrees Celsius, rendering the planet a cold, uninhabitable place. However, greenhouse gases are a double-edged sword. For millions of years, their levels in the atmosphere were regulated by natural processes such as volcanic eruptions, the decay of organic matter, and the carbon cycle. Yet, in recent centuries, human activities have disrupted this natural balance. Burning fossil fuels like coal, oil, and natural gas is the primary source of CO2 emissions, the most common greenhouse gas. Additionally, industrial agriculture, especially livestock farming, has significantly increased CH4 emissions, a gas with 25 times the heat-trapping potential of CO2 in the short term. Deforestation, a major driver of vegetation loss, has reduced the planet's capacity to absorb CO2. As a result, greenhouse gas levels in the atmosphere have risen dramatically, amplifying the natural greenhouse effect and leading to global warming. The global average temperature has risen by over 1.1 degrees Celsius compared to pre-industrial times, and this trend continues at an alarming rate. This increase not only affects the climate, but also directly impacts ecosystems and human lives. Melting ice at the poles, rising sea levels, prolonged droughts, and severe floods are just a few of the many serious consequences we are facing. Greenhouse gases like CH4 are particularly concerning. Although CH4 remains in the atmosphere for a shorter time than CO2, it is far more effective at trapping heat. Major sources of CH4 emissions include landfills, where organic waste decomposes, and livestock farming, where ruminant digestion releases large amounts of the gas. N2O, another often overlooked greenhouse gas, also has a significant heat-trapping effect and contributes to ozone layer depletion. It is primarily emitted from the use of chemical fertilizers in industrial agriculture. One striking example is that atmospheric CO2 concentrations have surpassed 420 parts per million, the highest level in 800,000 years, according to data from ancient ice cores. A more relatable example is the increasing CH4 emissions from livestock farming and landfills, sources often underestimated, but which contribute significantly to total greenhouse gas emissions. These examples underscore that, in addition to major industries, everyday activities can also have long-term impacts on the climate. Greenhouse gases are an integral part of Earth's natural system. They have helped maintain the planet in a livable state for billions of years. However, the unchecked rise of these gases due to human activities is putting the planet in a state of emergency. Without timely action, global temperatures could rise by an additional 1.5 degrees Celsius to 2 degrees Celsius in the coming decades, leading to irreversible consequences. Looking ahead, we must take strong measures to reduce greenhouse gas emissions, from adopting renewable energy and improving energy efficiency to changing individual consumption behaviors. Acting now is not only a responsibility to the planet, but also the key to securing the future for humanity and all living beings on Earth. Do you realize that stronger storms, record-breaking heat, and rapidly melting polar ice are direct consequences of climate change? Climate change is not just an environmental issue, but a global crisis with increasingly severe consequences. One of its most visible effects is the melting of polar ice. Massive ice sheets in Greenland and Antarctica are melting at unprecedented rates, releasing vast amounts of water into the oceans. This has caused sea levels to rise by an average of 20 centimeters over the past century, with projections indicating an additional rise of up to 1 meter by the end of the 21st century if global temperatures continue to increase. Low-lying areas such as the Maldives and densely populated coastal regions are at risk of being submerged, forcing millions into homelessness and mandatory migration. Beyond melting ice and rising sea levels, climate change is also intensifying the frequency and severity of extreme weather events. Stronger storms with higher wind speeds and heavier rainfall have become more common, causing significant damage to lives and property. Prolonged heat waves during the summer pose threats to human health, especially in urban areas where the heat island effect exacerbates already high temperatures. Droughts are becoming more severe, depleting water supplies and reducing agricultural yields, putting millions at risk of food insecurity. Additionally, flooding caused by heavy rainfall, as exemplified by the catastrophic floods in Pakistan in 2022, highlights the devastating impact of climate change. This historic flood affected millions, destroyed infrastructure, and caused severe economic losses. Climate change does not spare even developed nations. Hurricane Ian in the United States in 2022 caused tens of billions of dollars in damage, leaving many areas severely impacted. Extreme weather events not only disrupt daily life, but also threaten food and water security for millions of people. Prolonged droughts in certain regions lead to sharp declines in crop yields, driving up food prices. Conversely, flash floods can wipe out entire harvests, further crippling economies in agriculture-dependent nations. These consequences create a vicious cycle, especially in vulnerable regions with limited resources to combat such crises. Melting Arctic ice also transforms the region's entire ecosystem. As the ice disappears, species such as polar bears, seals, and penguins lose their habitats and face the risk of extinction. Moreover, melting ice releases methane, a potent greenhouse gas, from permafrost, exacerbating global warming. These dangerous feedback loops are pushing Earth into a self-reinforcing cycle of rising temperatures, which will be increasingly difficult to reverse without immediate action. In this context, understanding and addressing climate change has become a global imperative. Measures such as reducing greenhouse gas emissions, transitioning to renewable energy, and improving community resilience must be implemented immediately. Nations need to cooperate more closely to achieve international climate goals, such as the Paris Agreement, to limit global temperature increases to below 1.5 degrees Celsius. The consequences of climate change are not just abstract statistics, but a reality manifesting in our daily lives. From polar ice melt to devastating floods and droughts, its effects touch every aspect of the environment and society. The urgent need for decisive action is not only the responsibility of governments, but also of individuals to safeguard the planet for future generations. Could technology be the key to reversing the effects of climate change and saving the planet from the climate crisis? In response to the severe consequences of climate change, many scientific and technological solutions have been developed to reduce greenhouse gas emissions into the atmosphere. One of the most effective methods is the use of renewable energy, such as solar, wind, and hydropower, to replace fossil fuels. Renewable energy not only cuts CO2 emissions, but also reduces reliance on unsustainable energy sources, paving the way for a greener and cleaner future. Solar and wind energy are becoming increasingly popular alternatives thanks to declining production costs and improved efficiency. Solar farms and wind farms not only provide clean energy, but also create jobs for millions of people worldwide. In Vietnam, the implementation of solar energy projects has significantly reduced emissions while providing stable electricity to millions of households, a clear demonstration of renewable energy's potential in combating climate change. In addition, carbon capture and storage (CCS) technology has emerged as a groundbreaking solution to deal with CO2 emissions from industrial plants. CCS works by capturing CO2 at its source, compressing it, and storing it deep underground in geological formations, preventing it from entering the atmosphere. This technology is seen as an effective way to reduce emissions from heavy industries where transitioning to renewable energy remains challenging. The Boundary Dam CCS project in Canada is a prime example, showing that CCS is not only feasible, but can also play a crucial role in large-scale greenhouse gas reduction. However, CCS technology faces several challenges. High installation and operational costs make widespread deployment difficult, especially in developing countries. Moreover, further research is needed to ensure CO2 can be stored safely over the long term, minimizing the risk of leaks back to the surface. Alongside high-tech solutions, innovations in sustainable agriculture and forest restoration are also essential strategies. Modern industrial agriculture is a major source of CH4 emissions, but new farming practices such as regenerative agriculture and proper soil management can help reduce these emissions. Meanwhile, forest restoration, especially in tropical areas like the Amazon, acts as a natural carbon filter, absorbing large amounts of CO2 from the atmosphere. Protecting and expanding forest areas not only helps reduce greenhouse gases, but also preserves biodiversity and safeguards clean water resources. Examples from the original file highlight that CCS projects are being widely implemented in Europe and North America, demonstrating a strong commitment to leveraging technology to reduce greenhouse gases. In Vietnam, solar energy farms, such as those in Ninh Thuan province, not only bring economic benefits, but also significantly reduce emissions, showcasing the synergy between technological and sustainable solutions. The solution to the climate crisis lies not only in reducing emissions, but also in investing in groundbreaking technologies and changing the way we manage natural resources. Achieving this goal requires global cooperation among governments, businesses, and communities. Only then can we mitigate the impact of greenhouse gases, protect the planet, and ensure a sustainable future for future generations. Technology and science, when used effectively, will be the key to addressing one of humanity's greatest challenges. Death of the Earth scenarios. For the end of Earth in the future. Have you ever wondered if Earth, despite its billions of years of existence, could remain a perpetual haven for life? Although Earth currently maintains ideal conditions for life to thrive, like all celestial bodies in the universe, this blue planet also has a life cycle shaped by astronomical, climatic, and internal factors. Scientists affirm that over time, these ideal living conditions will not last forever. Since its formation around 4.5 billion years ago, Earth has undergone numerous major transformations. Initially, it was a scorching planet, with a surface covered in molten lava. After millions of years of cooling, water began to emerge, creating conditions for life to form and evolve. However, these transformations did not end there. Earth continues to be profoundly influenced by astronomical factors such as orbital movements, gravitational forces from other celestial bodies, and changes in the Sun, Earth's primary energy source. These factors not only affect the climate, but also play a role in determining the planet's lifespan. Earth's internal dynamics also play a crucial role. Geological activities like volcanism, plate tectonics, and heat transfer from Earth's core help sustain the carbon cycle and current living conditions. However, the energy within Earth's core is not infinite. As the core gradually cools over time, geological activities will diminish, leading to climatic imbalances. This could drastically alter the planet's landscape. Additionally, large climatic cycles, such as ice ages and global warming phases, demonstrate Earth's constant changes. Human activities, including industrialization and resource extraction, have accelerated climate change. Yet even without human intervention, natural laws would continue to shape the planet's destiny. The gradual expansion of the Sun, projected to occur in about 5 billion years, will raise Earth's surface temperatures to levels where liquid water cannot exist. This suggests that life, if it still exists by then, will no longer be sustainable on this planet. The original file compares Earth's life cycle to that of neighboring planets like Venus and Mars, vividly illustrating the shared fate of planets. Mars, which once showed evidence of liquid water, is now a cold desert. Venus, which may have once had a temperate climate, has become a hellscape with a dense carbon dioxide atmosphere and temperatures high enough to melt metal. These transformations demonstrate that no planet can maintain living conditions forever, even if they once had ideal phases. Earth's future is no exception to this rule. The Sun, currently in its stable phase, will eventually run out of fuel and enter its red giant phase. At that time, the planets in the solar system will undergo major changes, and Earth, no matter how resilient, will not escape a fate of complete transformation. These changes could result in the total loss of the atmosphere and surface, rendering the planet uninhabitable. Earth is but a small part of the vast cosmic picture, where every planet is subject to natural and cosmic forces. Change is inevitable, and ultimately, the blue planet we call home will also come to an end. Yet, understanding this life cycle helps humanity appreciate what we have while motivating efforts to protect and sustain the planet during the time we can still influence its fate. What will happen when the light of life for Earth, the Sun, becomes the catalyst for the planet's destruction? The Sun, the energy source sustaining life on the blue planet, is not an unchanging entity. Like all stars in the universe, the Sun has its own life cycle and is gradually evolving. Currently, it is in a stable phase, emitting just enough radiation to support Earth's rich ecosystems. However, in 1 to 2 billion years, the Sun will enter its mature phase, becoming brighter and hotter. These changes will trigger irreversible consequences, rendering Earth uninhabitable. When the Sun becomes approximately 10% brighter than it is today, predicted to occur in about 1 billion years, the surface temperature of Earth will rise significantly. This will initiate a series of catastrophic reactions, starting with massive water evaporation. Earth's oceans, rivers, lakes, and freshwater sources will begin evaporating rapidly due to the increasing heat. As water vapor fills the atmosphere, it will act as a potent greenhouse gas, trapping heat and causing surface temperatures to rise even further. This creates a dangerous positive feedback loop. Higher temperatures cause more water to evaporate, and water vapor continues to raise temperatures, ultimately leading to the complete disappearance of all water on Earth. This phenomenon will not only affect water, but also threaten the planet's atmosphere. Under the intense radiation from the sun, atmospheric molecules will be broken down. Specifically, solar radiation will decompose water molecules into hydrogen and oxygen. Because hydrogen is an extremely light element, it will easily escape into space, depleting a vital component of the atmosphere. Over millions of years, this process will erode Earth's protective atmosphere, leaving the planet unable to sustain life. Eventually, Earth will become a barren, scorching world, much like Venus today. Venus serves as the closest real-world example of Earth's potential fate. In the original file, scientists compare the future evaporation and atmospheric loss of Earth to the runaway greenhouse effect on Venus. Venus may once have had liquid water, but the sun's heat, combined with extreme greenhouse conditions, caused all the water to evaporate. Venus's current dense carbon dioxide atmosphere keeps its surface temperature above 450 degrees Celsius, hot enough to melt metals like lead. The disappearance of water and the atmosphere on Earth would not only be a natural disaster, but also mark the end of all ecosystems and life on the planet. Plants, animals, and humans, all of which depend on water and the atmosphere, would be unable to survive under such conditions. The cradle of life would be erased, leaving Earth as a desolate, barren planet in the solar system. Though this scenario lies far in the future, it is a stark reminder that nothing in the universe is eternal. The sun, which plays the central role as Earth's life-giver, will gradually become the agent of the planet's destruction. This serves as a powerful reminder of the fragility of life and the importance of protecting our planet in the present. In Earth's billions of years of existence, life has occupied only a fleeting yet incredibly precious moment. Understanding this inevitable fate makes us cherish what we have even more, while pushing us to explore solutions to extend humanity's existence beyond the limits of this planet. Can you imagine that in the distant future, Earth could be pulled into a cosmic void, completely disappearing without a trace? Although Earth is currently a safe and vibrant home, in billions of years, the blue planet will face terrifying astronomical scenarios that could lead to its complete destruction. These scenarios are not mere products of imagination, but the results of physical laws and cosmic phenomena we have observed in reality. One of the most evident apocalyptic scenarios is when the sun enters its red giant phase, expected to occur about 5 billion years from now. At that point, the sun will exhaust the hydrogen fuel in its core and begin burning heavier elements, causing it to expand to hundreds of times its current size. According to scientists, this process will result in the sun engulfing nearby planets like Mercury, Venus, and possibly even Earth. The immense heat and powerful gravitational forces of the sun at that stage will cause Earth to either melt or vaporize entirely, leaving only cosmic dust in the remnants of the star. Apart from the red giant scenario, Earth also faces the risk of astronomical collisions. The planet's history shows that such events are not uncommon. About 4.5 billion years ago, a massive collision between early Earth and a Mars-sized celestial body formed the Moon. More recently, around 65 million years ago, an asteroid approximately 10 kilometers in diameter struck Earth, causing the extinction of dinosaurs and drastically altering the planet's ecosystem. In the future, similar collisions on a larger scale could completely obliterate Earth. A rogue planet or a supermassive asteroid entering Earth's orbit could cause an explosion so immense that it would erase the planet from the cosmic map. Even if Earth survives these scenarios, other cosmic forces could still lead to its complete annihilation. A black hole, one of the most feared phenomena in the universe, could consume Earth if it strays too close to the solar system. For example, Sagittarius, a star, the black hole at the center of the Milky Way, has the potential to influence the orbits of celestial bodies within a range of tens of light years. Additionally, nearby supernova explosions, which release intense shock waves and gamma radiation, could destroy Earth in mere seconds. Real-world examples from the universe help us better visualize these destructive possibilities. The original file detailed the Sun's expansion during its red giant phase and its potential to engulf nearby planets. Another illustration is the astronomical collision between comet Shoemaker-Levy 9 and Jupiter in 1994. This impact created explosions millions of times more powerful than atomic bombs, demonstrating the immense force of cosmic events. The distant future of Earth is far from a tranquil story. The blue planet will face inevitable astronomical scenarios, underscoring that even long-lasting and resilient celestial bodies like Earth are but small components of the vast cosmic picture. These scenarios not only illuminate the workings of astronomical laws, but also remind us of the fragility of the planet we call home. While these events lie far in the future, they raise profound questions about humanity's role in protecting Earth and preparing for challenges beyond our control. The impact of the Sun becoming a red giant star. What will happen when Earth's light of life, the Sun, suddenly expands into a monstrous giant, engulfing the solar system? This is not a fictional scenario, but an inevitable phase in the Sun's life cycle. Currently, the Sun is in a stable phase called the main sequence. During this phase, hydrogen fusion in the core produces stable energy, providing the light and heat necessary for life on Earth. However, this process cannot last forever. In approximately 5 billion years, the hydrogen fuel in the Sun's core will run out, marking the beginning of profound changes. When hydrogen is no longer sufficient to sustain nuclear fusion, the Sun's core will start to contract due to gravitational forces. This contraction will raise the core's temperature enough to ignite helium fusion, a new type of fuel. The transition from hydrogen to helium fusion will trigger a series of powerful effects on the Sun's structure. The outer layers of the Sun will expand significantly, transforming it into a red giant star. During this phase, the Sun's size could increase by 100 to 200 times its current size, with its radius extending to the orbit of Venus, or even farther. At this point, the Sun will become an enormous star, radiating brilliantly, but with a cooler surface temperature than it has today. However, the immense heat from the Sun will intensify, severely impacting the planets of the solar system. Mercury and Venus, the two closest planets to the Sun, will be entirely engulfed in the fiery giant's layers. Earth, while potentially outside the Sun's gaseous outer shell, will still face devastating consequences. The extreme heat will evaporate all water on Earth's surface, turning the blue planet into a barren desert, much like Venus today. The surface rocks and minerals on Earth could melt, transforming the planet into a desolate molten sphere. Furthermore, the intense light and radiation from the Sun during its red giant phase will utterly destroy Earth's atmosphere, stripping away the only shield protecting it from cosmic radiation. Life, if it still exists at that point, will have no chance of survival. This phase will mark the definitive end of Earth as a life-supporting planet. The red giant phase of the Sun mirrors the evolution of other stars in this stage, such as Betelgeuse, a supergiant red star in the constellation Orion. With a diameter thousands of times larger than the Sun, Betelgeuse provides a vivid example of how stars transform in their final life cycle phases. Another example is Aldebaran, a bright red star in the constellation Taurus, currently in its red giant phase. Astronomers have observed Aldebaran's expansion, offering insights into the fate that awaits the Sun. The Sun's transition into a red giant is not only part of its natural life cycle, but also the beginning of a sequence of events that will permanently alter the solar system. While this process is billions of years away, it demonstrates that nothing in the universe is eternal. The fate of the Sun and Earth is a stark reminder of the fragility and limitations of planets, even Earth, the planet we call home. Can you imagine that one day, all of Earth's oceans could evaporate in an instant under the scorching heat of the Sun? This is a scenario that could unfold when the Sun evolves into a red giant star, approximately 5 billion years from now. This phase marks a dramatic transformation in the star's life cycle, with its size swelling to hundreds of times its current scale, and its heat increasing significantly. The Sun's outer edges could then extend to Earth's orbit, or even beyond, rendering the blue planet an uninhabitable wasteland. The heat from the red giant Sun will trigger a series of catastrophic effects on Earth. First, the extreme temperatures will cause the entire ocean system to evaporate. Massive bodies of water, from the Pacific to the Atlantic, will turn into water vapor and rise into the atmosphere. This immense amount of water vapor will saturate the atmosphere, creating a dense greenhouse gas layer that leads to an uncontrollable greenhouse effect. This phenomenon will not only further increase temperatures, but also completely halt Earth's natural cooling processes, pushing the planet into a destructive feedback loop. Beyond the evaporation of oceans, the Sun's heat will drastically alter Earth's surface. The once solid layers of rock will melt into molten lava under the intense heat. The planet's surface will lose its green forests and blue waters, transforming into a glowing, barren red sphere, resembling Venus as it appears today. Earth's already fragile ecosystems will be entirely obliterated, leaving no trace of the life that once flourished here. Another grave consequence during this phase is the loss of Earth's atmosphere. The intense heat and radiation from the Sun will break down the molecular structures of the gases in Earth's atmosphere. Oxygen and nitrogen, the two key components that sustain life, will be pushed into space. The atmosphere, which acts as Earth's shield against cosmic radiation, will vanish, leaving the planet exposed and defenseless against the harshness of the universe. As the Sun enters its red giant phase, Earth's surface temperatures could exceed 2,000 degrees Celsius, a heat level sufficient to melt metals and destroy all material structures. A similar phenomenon can be observed in the red giant star Antares, where the powerful radiation has completely stripped the atmospheres of nearby planets. This process exemplifies the overwhelming force of a red giant star in reshaping the fate of surrounding planets. When the Sun transitions into a red giant, Earth will no longer be a habitable planet. Oceans will evaporate entirely, the planet's surface will burn to ashes, and its atmosphere will be completely destroyed. This is an unavoidable chapter in the life cycle of the solar system, a testament to the unforgiving nature of cosmic laws. In the distant future, the blue planet we call home will become a dead world, consumed by the very source of life that once sustained it, the Sun. What will happen when the Sun, once the radiant source of life on Earth, becomes a faint and dim light in the vast expanse of space? This is the inevitable scenario as the Sun reaches the end of its life cycle, transitioning from a red giant phase to a white dwarf. This transformation not only marks the demise of the Sun itself, but also signals the near-total disappearance of Earth in the vast cosmos. When the Sun exhausts the helium fuel in its core after its red giant phase, gravitational forces will cause the core to collapse into a small, dense celestial body known as a white dwarf. Unlike its current state, where the sun shines brightly due to nuclear fusion, the white dwarf will merely be a remnant emitting faint light, incapable of sustaining life on any planet in the solar system. If Earth still exists by this time, it will face monumental changes. Much of the sun's mass will have been expelled into space as strong stellar winds during the red giant phase, reducing the gravitational force that keeps the planets in orbit. Consequently, Earth may be pushed farther away from the sun or might even escape its orbit entirely, becoming a wandering planet in the cold and dark void of space. Even if Earth remains in orbit around the white dwarf, it will no longer be recognizable. During the previous red giant phase, Earth's surface will have been scorched, its oceans evaporated, and its atmosphere obliterated. At this stage, what remains of Earth will be a barren, rocky core subjected to radiation and stellar winds, gradually disintegrating into small particles of dust. These fragments, if not scattered into the depths of space, could form a thin debris disk around the white dwarf, similar to the material disks observed around other star systems. To astronomers, white dwarfs symbolize both endings and beginnings. A prime example is Sirius B, a well-known white dwarf in the Sirius binary star system. Studies of Sirius B have shown that planets or materials surrounding a white dwarf are often destroyed and dispersed into space. This serves as a glimpse into Earth's fate. What was once a vibrant planet teeming with life will dissolve into cosmic dust, merging with the galactic flow. The sun's journey ends as it contracts into a white dwarf, and with it, Earth's existence will also conclude. What was once a lush, life-supporting planet for billions of years will vanish from the astronomical timeline. This fate serves as a stark reminder of the impermanence of all things in the universe, affirming that even the greatest phenomena are destined to fade and disappear in the grand orchestration of the cosmos. In a brief moment, a colossal explosion occurred, and the entire universe emerged instantaneously. Countless wonders unfolded in this instant, leaving us astonished. How is it that we exist here? And where did the universe come from? The mystery of creation, the secrets behind everything, all lie within that very first moment. Today, technology is reaching the threshold of exploring what happened during this most critical instant of all. In the beginning, there was nothing. No matter, no energy, not even empty space, as space itself had yet to come into existence. There was no concept of time, for there was nothing to measure it by. From this void, a fireball, smaller than an atom and hotter than the core of the sun by trillions of times, suddenly appeared. Everything that makes up the universe exploded from a point far smaller than the tip of a needle. Time began, and within a brief second, the blueprint for the entire universe was laid out. How this happened remains one of the greatest mysteries. Professor Lawrence Krauss has dedicated his career to studying the first moments after the Big Bang, helping us to better understand the universe. To truly grasp our place in the cosmos, we must journey back to the origin and uncover how everything came into being. Reflecting on the moment the universe was born is a revolutionary idea. Although the Big Bang theory is widely accepted today, the concept only gained recognition less than a century ago. It's important to remember that our knowledge of the universe is still very new. Just 80 years ago, the scientific community still believed that the universe was static and eternal. However, this understanding changed in 1929 at the Mount Wilson Observatory in California, when Edwin Hubble studied light from distant galaxies. He observed that the farther a galaxy was, the longer the wavelength of the light it emitted became. As light travels farther, it stretches, altering its wavelength. This principle is similar to what happens with sound waves. When a train approaches, the pitch of its whistle is higher. As it moves away, the pitch drops. Each successive sound wave must travel farther to reach you, stretching out the sound and lowering its pitch. A similar phenomenon occurs with light. Hubble's observations led to a groundbreaking conclusion. The universe is expanding. This revelation marked a fundamental shift in our understanding of the cosmos, suggesting that the universe had a beginning, a point at which it all began from nothing. As we continue to study the universe's origins, we find ourselves contemplating that original moment, piecing together clues from that explosive birth, each discovery propelling us closer to understanding our place within this grand cosmic design. With ongoing advancements in technology, we stand on the edge of unraveling one of the most profound mysteries of existence, the mystery of the universe's birth. When a galaxy moves away from us, its light waves stretch, becoming longer and shifting toward the red end of the spectrum. This phenomenon is called redshift. In visible light, red occupies one end of the spectrum, while blue is at the opposite end. Red light has long wavelengths, while blue light has shorter ones. When we observe the universe, we see light from distant stars stretching, making it appear redder. And the farther away these stars are, the more pronounced this red hue becomes. All galaxies around us exhibit this redshift, indicating they are moving away. Looking in every direction toward distant galaxies, we find they are all moving away from us, most traveling at speeds of up to 1,000,000 miles per hour. If galaxies are moving apart, then at some point they must have been closer together. This observation suggests that the universe is expanding from a single point, providing the first evidence that the universe had a beginning. Hubble's discovery paved the way for a revolutionary concept, the Big Bang Theory. Scientists believe that in the first second after the Big Bang, the elements that make up every star and planet in the universe were formed. To validate this theory, scientists needed a new way to measure time. We're talking about minuscule fractions of time, far smaller than any standard measure we use in other fields, smaller than the time of a racing car lap or a sprinter's sprint, or any other conceivable event. In fact, we've realized that countless events can occur within just a fraction of a second, happening so quickly it's almost beyond comprehension. Hours, minutes, and seconds form the basis of modern life. Yet the events following the Big Bang occurred in much smaller intervals than anything we are familiar with. To analyze these events, scientists use a new unit of time called the Planck time. 1 Planck time is equal to 10 to the negative 43rd power seconds, a staggeringly tiny measure consisting of a decimal point, 42 zeros, and then a 1. Although it's an extremely short duration, within the first beat of Planck time, an event that shaped the next 13.7 billion years took place. From that primordial fireball, 4 fundamental forces of nature emerged, forces that underpin everything around us. Gravity helps form stars and planets, governs the moon and tides, and keeps us grounded on Earth. Electromagnetic force lights up cities, connects phones, and powers computers. 2 nuclear forces, strong and weak, bind particles within our bodies and fuel the sun's fire. We exist because of these 4 forces, created in the universe's first seconds. Without them, the universe would remain an amorphous cloud of radiation. Without these forces, nothing would happen. No television, no sports, no love, no hate, no human drama, and none of the things that make life meaningful. But in that first beat of Planck time, the 4 forces were a unified entity called superforce. Gravity, nuclear forces, and electromagnetism were not yet separate. Physicist Michio Kaku likens this separation process to a crystal. a perfectly symmetrical crystal where all forces are united in sublime simplicity at the dawn of time. As the cosmic clock ticked one more beat of Planck time, the universe, once a tiny fireball, began to expand, and the four forces gradually separated. This process is similar to rapidly cooling a superheated crystal, with cracks forming as it breaks into distinct parts. The first fragment to separate was gravity, followed by the nuclear forces, and finally, from the initial superforce, we were left with a dispersed gem. These four fragments continue to operate to this day. Gravity holds Earth in its orbit, nuclear forces fuel the sun, and electromagnetic radiation keeps us connected. Today, these forces still shape every aspect of our existence. Gravity keeps our feet on the ground, holds Earth's orbit, and allows the universe to be structured. Electromagnetic force drives our technology, lights our cities, and powers our devices. The strong and weak nuclear forces govern the particles within our bodies and allow stars to burn, providing energy for life as we know it. All this from a single unified force, evolving through cosmic time, and now fragmented yet harmonized in the workings of the universe. In this unified structure, we find the foundation of everything we know, and its evolution continues to influence our lives, drawing us closer to understanding the origins of existence itself. The light illuminating our planet represents only fleeting moments in a vast journey, as the foundation of the world began forming in those initial seconds. At that time, the universe was merely a fireball smaller than an atom, with temperatures reaching trillions of degrees. To explore the universe's expansion, scientists use incredibly powerful telescopes, allowing them to peer back in time. When astrophysicist David Spergel gazes up at the sky, he sees history unfolding. Observing space is essentially observing time, as light travels at a finite speed. Light from the sun, for example, takes about 8 minutes to reach Earth. So we see the sun as it was 8 minutes ago, not as it is now. When we look at the night sky, the nearest stars could be 10 to 20 light years away, showing us their past from decades ago. The deeper we gaze into space, the farther back in time we travel. The Big Bang was so unimaginably powerful and hot that traces of its initial heat still linger today. This primordial heat began as super-hot X-ray radiation. Over time, as the universe expanded and cooled, the radiation stretched into visible light, then shifted to microwaves, and finally to radio waves. These faint remnants of energy, known as the cosmic microwave background, CMB, radiation, constantly bathe the Earth. The CMB is nothing less than the echo of creation itself, the embers, the afterglow of the Big Bang's explosive birth. If we could see microwaves with our eyes, the night sky would light up with a cosmic display, revealing the Big Bang as a radiant explosion spanning the heavens. In fact, you can glimpse a trace of this ancient radiation with something as simple as a television. Switch an old TV to a channel of static, and a small percentage of that static is radiation left over from the Big Bang. This tangible connection to the universe's origin is a profound testament to its beginnings. The CMB doesn't just connect us to the Big Bang, it also holds clues about the universe's early evolution. Within a trillionth of a second after the Big Bang, the universe entered a dramatic new phase. Scientists describe this rapid transformation as inflation. During inflation, the universe expanded exponentially, growing from a size smaller than an atom to that of a baseball in an instant. This single moment of extraordinary growth accounts for more expansion than the entire 13.7 billion years that followed. Remarkably, the evidence for inflation survives in the uniformity of the CMB. This radiation is startlingly even, with the same temperature in every direction, presenting scientists with a puzzle. How could such uniformity exist unless the universe had expanded at speeds far exceeding that of light? Inflation provides the answer. It suggests the fireball universe inflated evenly, like a balloon expanding with a single powerful breath of energy. To imagine inflation, think of compressing a spring. The more you press it down, the more energy you store. When you release it, that energy bursts out all at once, causing an explosive release. Similarly, the energy stored in the early universe drove this astonishing, exponential expansion of space. Inflation left the universe astonishingly uniform, setting the stage for the formation of galaxies, stars, and planets. These faint ripples in the CMB tell the tale of how the universe expanded from its fiery infancy into the vast cosmos we observe today. The journey from a blazing speck to the magnificent universe is nothing short of extraordinary, and every detail etched in the CMB serves as a window into that awe-inspiring process. From the very first second after the Big Bang, the universe embarked on an extraordinary journey of transformation. Galaxies, stars, and planets didn't just appear. They were born through a fascinating process, beginning as clusters of particles. Over time, these particles clumped together under the relentless pull of gravity, forming dense masses. Earth itself began as one of these clusters, a ball of particles that merged through friction and gravitational forces. Even the Sun, which sustains life on our planet, originated as a sprawling cloud of gas and dust. But how did these clusters form in the first place? The early universe, by all accounts, should have been lumpy and uneven, a chaotic soup of matter and energy. To unravel this mystery and connect the formation of stars and planets to that very first second, NASA scientists, including David Spergel, launched an ambitious mission. They developed the Wilkinson Microwave Anisotropy Probe, WMAP, a groundbreaking satellite designed to measure the temperature of cosmic radiation with unprecedented precision. Cosmic radiation, though present everywhere, is faint and difficult to observe in detail. To overcome interference from Earth, WMAP was positioned 1 million miles away in space. In 2001, the mission began with the dramatic launch of the Delta II rocket. The tension and excitement of seeing the spacecraft lift off were palpable, and the realization that it was functioning perfectly brought a sense of awe and relief. For 5 years, WMAP tirelessly scanned the heavens, orbiting the Sun while keeping the Earth behind it. The satellite spun rapidly, mapping the leftover radiation from the Big Bang in exquisite detail. Covering about 1/3 of the sky every hour, WMAP produced the most detailed temperature maps of cosmic radiation ever seen. The resulting data was nothing short of remarkable. Tiny variations in temperature were revealed across the entire sky, visualized as blue and red patches on the map. The cooler blue regions were tens of thousands of degrees colder, while the slightly warmer red regions hinted at areas of greater density. These minute ripples in temperature represented the seeds of structure in the early universe, regions where matter began to cluster under the influence of gravity. Over billions of years, these tiny clusters grew, eventually forming stars, galaxies, and planets.